Namaskar, sir. Good afternoon, sir.
Good afternoon.
I am Rupavalli, sir. Hi, sir. How are you, sir?
Fine, fine. That is going to start.
Yes. Let me start now, sir. Shall I start, sir? Sir, shall I start, sir?
Oh, sorry, I am not the chairperson of this session. Actually, this is my time to talk. So I'm sorry, you please have to wait for someone from
Okay,
the
sir.
organization
Okay.
team. Yeah,
Okay, sir. Okay,
yeah,
sir.
yeah, they will guide you.
Okay, sir.
হ্যালো সুব্রত। Hola, আরেকটা প্লেট লয়ে আয়। হ্যালো।
Hello, good afternoon, sir.
হ্যালো, গুড আফটারনুন।
I'm Rupavalli, sir. Shall I start the presentation? My presentation, ma'am? PL4, sir, PL4.
Hello, am I audible?
Yes, sir. Audible, sir.
Okay. Uh, Good afternoon to all. It's my privilege to introduce Professor Shantanu Ghosh. Though he is a renowned professor of physics in today, I am just introducing him, uh, Dr. Shantanu Ghosh, Professor, Department of Physics, Indian Institute of Technology, Delhi, New Delhi. India is actively involved in the research activities related to magnetic semiconductors, magnetic material insulator, nano composites, nanostructured carbon and nanohybrids, nanoscale energy materials, and ion material interaction. He is an editorial board member of Scientific Report, Nature Portfolio, Scientific Review, Springer, Nature, member of International Alliance of Societies for a Sustainable Future, life member, Materials Research Society, MRS, Magnetic Society of India. He also worked as national coordinator and national coordination committee member of PMRF, Government of India, and joined the team of Unnat Bharat Abhijan at IIT Delhi. He has authored 2 books, 11 book chapters, and review articles, developed and coordinated 2 NPTEL, and published about 150 research papers. He has delivered more than DST BMBF Fellow in the year 2000, DST DFG Fellow in the year 2006, DAAD IIT Fellow in 2010 and 2024.
হ্যালো শান্তনুদা,
Hello, Mihir.
প্লিজ স্টার্ট ইউর টক।
So, shall I share the slides? Okay. Yeah, thank you.
So shall I start? Hello.
Hello,
Then now okay. Hello.
shall I start? Mihir? Hello.
Yes, sir. Yes.
Yeah, slides are visible. I go to slideshow mode. Is there any connection issue?
Sir,
Am I audible?
yes, sir.
Okay, so I start. Okay.
Yes, sir.
Okay, thanks a lot, Professor Meir, for introducing me in this event. I'm thankful to Professor Nath, Principal, Women's College, Professor Dev, and Professor Bhaumik, and other members of the organization team for inviting me in this event. I am going to present our works on nanocomposite and nanohybrid. It's almost about 2 decades of work which we had done at IIT Delhi. And it started from a basic research and up to a stage of device development. Gratitude to my alma mater, Umaganta Academy, MBB College, University of Hyderabad, and Inter-University Accelerator Center. And of course, my institute, IIT Delhi. I would just like to show you a few slides on recent progress and mission of my institute, IIT Delhi. And when I joined it, we had a mission which was known as Nano Mission from Department of Science and Technology. And we started some development of equipment, facilities at IIT Delhi. And now we have a facility called Nanoscale Research Facility. And you can see we have all synthesis, fabrication facility of nanoscale material and nanoscale devices, and some researchers who are working in the clean room. And it's a user facility, so anyone can use this facility. It's available in the website, IIT Delhi website. We have started our activities on National Quantum Mission, NQM, which is also a mission of DST, and some of the other institutes who are also collaborating us in this particular mission. It is at a starting phase. And also, we, you know that we have in India, we have the India Semiconductor Mission, or ISM. IIT Delhi is playing a very good role in this mission also. There are some laboratories, specialized laboratories have been developed for this mission. Like we have microelectronics lab, advanced electrical characterization facility, epitaxial semiconductor device lab, etc. And then we have a central research facility. IIT Delhi is actually, we have two campuses now. One campus is in the main city of Delhi. Another campus is at Sonipat, Haryana. And that in that campus, we have most of the central research facilities, equipments have been, we have established there. And the important part of this is that we had a program called Sophisticated Analytical and Technical Help Institute, SATI. It is for advanced equipment access for academia, startup, and industry based on training, equipment, laboratory, conference, workshop, and all these things. And anyone who wants to use this facility can go to this website and get access to these facilities. If you have any issue and if you want to use this facility, you can just directly send me an email. I will introduce you with the person or the coordinator of any facility which you require. We also have a high performance computing facility at IIT Delhi. Those who are doing simulation and theoretical studies in physics, chemistry, biology, and all these areas of science and engineering. It is open to students, faculty, and researchers from IIT Delhi, of course, and other external academic and research institutes. You can find this description of this facility in our website, and if you are interested to use these facilities, it's a highly supercomputer-based facilities with AI, ML, and everything is inducted in this facility. So it's a good facility to use. We have a laboratory which is working, in a collaborative manner with DRDO, but there is certain confidential thing here, and I'm not very much actively involved with this facility, but there are many faculty members who are working in this project. I have recently joined another mission, which is that IIT Delhi is naturally coordinating. This is very interesting because, the government of India has a mission called Unnat Bharat Abhiyan. The idea of this mission is that to create an interface between the villages, and higher educational institute. So a rough number, if we look at it, we have almost 7 lakh villages in India and closely around 45,000 higher education institute. So the idea is that how to develop or make a rural development plan through the knowledge of science and technology of this higher education institute. So almost in every state, we have the coordinator, and in Tripura, I think at NIT Agartala, we have a coordinator who is coordinating the villages, some of the villages nearby their institute. Now I come to my presentation outline. I'll just briefly introduce about what is known as nanoscale, and then the talk is divided in 2 parts. In the first part, I will talk about synthesis and basic characterization, and in the second part, I will discuss about application and some prototypes which we have developed after this basic research. So looking at this particular scale, we can understand what is the big and what is small. So it starts from exa, okay, which is 10 to the power 18, and it somewhere ends at 10 to the power minus 19, which is atto. So when we talk about nano-dimensional material, we are here at 10 to the power minus 9. This is actually typically one example of a nanomaterial, but if we go to bigger size, there is one material which is in minus 6, this is minus 3, this is 0, this is plus 3, plus 6, and plus 9. So it is scaled from minus 9 to plus 9, starting with a very small cholesterol molecules and a celestial of the sun. So this is what, and there are also bigger dimension, that there are also smaller dimension, and that we are in this dimension. Our research is at 10 to the power minus 9 meter scale. But it's really an interdisciplinary endeavor. Even at IIT Delhi, when we had started this particular research, chemistry, physics, biology, and different engineering departments, bio department, material science, IT, everybody joined together. And we used to have a lot of meetings, and then the nanoscale research facility evolved. And we get a very good platform here to collaborate through this nanoscale research facility within IIT and also outside IIT. So now I come to the first part of my talk, that is synthesis and basic characterization of nanocomposite and nanohybrids. So what is nanocomposite? Nanocomposite is a material where you have 2 phases, 2 materials of distinct phases. Suppose you want to grow some nanoparticle in a matrix, okay? So they retain their characteristic, but they are combined in one particular matrix. So our nanocomposite is some metal nanoparticle, nanodot, extremely small nanoparticle on an insulating matrix, and the insulating matrix we use is silica. Some of the nanoparticles which we use, nickel, iron, cobalt, gold, etc. So how do we grow this nanocomposite? We use a standard technique called sputtering. So this is the target where SiO2 is the target, where we glue these metal chips, and then from a atom source we shoot the SiO2 target as well as these metal chips. So by sputtering, they fall down, okay? And then we have a substrate with a substrate holder here, which is rotational in order to make a uniform film. And eventually what we get, nanoparticles embedded in SiO2 matrix. So there are certain deposition parameters which we follow. So once we get this film, we do a what is known as a composition analysis or identification of the material. So this is a Rutherford backscattering spectrometry, which gives us this identification, RBS. So nickel is, you can see this peak of nickel because it is nickel nanoparticle embedded in SiO2. So we have a sharp peak for nickel, and then silicon and oxygen. And one can also get the FWHM of this, and that also gives us the thickness as well as what is the percentage or concentration of nickel in this particular nanocomposite. In order to look at how small the particles are, transmission electron microscopy are done. And if you anneal these, increase the temperature, then eventually the size of this nanoparticle increases. So you can see there is a typical distribution of the nanoparticle. And you can also see that there is a contrast in color. That means that the insulating matrix is also appearing in this image. Now, generally, when we grow these nanoparticles are all spherical. So you can look at this TM image. So they're all spherical nanoparticle. Okay. We have to annihilate a little bit in order to grow the size of the nanoparticle. And then this is a typical distribution of the nanoparticle. Now, this is good. This is our sample, but sometimes you want to engineer the shape of this nanoparticle. This is required for some application, which I will come little later. But let me tell you how do we engineer the shape of this nanoparticle. So the engineering of the shape of the nanoparticle is done using an energetic ion. If energetic ion interacts, one can see that some particles actually remain spherical, some particles becomes elliptical. Okay, so if you do a transmission electron microscopy after this irradiation, you can very clearly see that many nanoparticles, they change their shape. They become elongated or elliptical. So spherical nanoparticles becomes elliptical with this high resolution TEM. And we try to understand this phenomenon, why they change the shape. So we take a model which was developed by Professor Marshall Toulemont from France. He's also one of my collaborators. So what he did, he actually developed two coupled differential equations, which contains an electronic term and a lattice term. It means that when ion interacts with the material, the electronic subsystem, it gets first the energy from the ion and goes to a very high temperature state transiently. And then eventually it gives it temperature to the lattice. And you can see the magnitude of the temperature which is there in the lattice. Almost it is more than melting point of the material. So that means transiently in a very small dimension, when this ion hits, actually a part of this entire matrix and the nanoparticle, they go to molten state. So if we try to understand it simply, there is an animation. So these are the nanoparticles which are embedded in the matrix. Pick up one nanoparticle here, shoot ion on this nanoparticle. Now what happened as per this calculation of Marshall, this temperature spikes takes place in the nanoparticle as well as the surrounding matrix. And then they go to molten state. So what happens after the particle passes through? It goes to the equilibrium state, and when it comes back to the equilibrium state, it changes its shape. So this is one set of materials which we grow, and these are the observations which I've already discussed. But in order to look at it more carefully from the electrical measurement, so what we do, we just do an in-plane and out-of-plane these IV characteristics. Okay, and you can see that in-plane IV characteristic, this is the current which is here at the green line, very small. But when you do out-of-plane, there is an enhancement in current. So this shows that there is an elongation of the particle. Okay, but this is a cluster which is taken in the DFT calculation, density functional theory. It tells that if we take a particle and we take it to a high temperature and then it quenches, if we quench it back, the particle does not retain its original spherical shape, it becomes an elongated shape. So it is also established by the simple experiment as well as by the density functional theory. Now I come to the second material. Second material is a nanohybrid. So nanohybrid is slightly different from nanocomposite. In nanohybrid material, there is actually a bonding between two materials. Okay, they are not independent phase. Okay, so when you grow a nanohybrid, there are some sort of interfacial bonding. So in nanohybrid, we grow initially carbon nanotube. These are one-dimensional nanomaterial. So we use simple thermal CVT technique, which we have developed in our laboratory, and we routinely grow carbon nanotube. So these are the TM images or HRTM images of carbon nanotubes. And this is a Raman spectrum of carbon nanotube, because carbon nanotube, there are two distinct features which comes in the Raman spectrum. One is this G peak, which is graphitic because it is a graphitic sheet which is rolled. And there is a D peak, which is a defect. So there are certain defects in the graphitic sheet. Okay, so that leads to some sp2 and sp3 hybridized carbon in the carbon nanotube. So once we grow the carbon nanotube, then we coat some oxide, sulfide, hexaboride nanoparticle, very small nanoparticle. And these are grown by chemical process. So this is complete chemistry by which the, here one example I am showing, neodymium oxide. There are some sulfide and hexaboride which also regularly our students grow in the lab. And then it is spin coated on MWCNT. So it's a very simple method by which we grow this nanohybrid. And then once we do it, it is important to look at or map the elements which are present in this nanohybrid. So you can see that it's a cross-sectional FACM where clearly these nanotubes are shown. They are even vertically aligned nanotube. And on top of that, you can see that small oxide coating, small nanoparticles of Nd2O3. And individual element, one can do mapping by energy dispersive X-ray or EDX and make sure what are the elements present in the material, and one can also get an approximate estimation of the atomic percent of each element in the material. So this is all about the first part, this material synthesis and basic characterization. And now I'll come to the applications and some prototypes we will discuss. With the first application which we had started with this nanocomposite is a very simple application, Hall effect. Hall effect is an experiment which we do at our UG or PG laboratory, and students are doing it. And we have also done it during our postgraduate courses. So what is Hall effect? Hall effect is an effect where you take a material, you apply a magnetic field perpendicular to current, which is flowing in another direction. And then perpendicular to both this magnetic field and current, a voltage develops. This is called Hall voltage. And why does it happen? It happens because when you apply this perpendicular magnetic field, it takes the charge carriers to one side. Okay, we know that Lorentz force acts there, is the force, and it takes electrons to one side, and another side we do not have electrons, so it creates a kind of voltage which is known as Hall voltage. Okay, it was discovered long back, but is routinely used in every laboratory where a magnetic field sensor is required. So if you have an electromagnet in your laboratory, you need a Hall sensor and a Gauss meter. So what it does, you have to place that Hall sensor in between these pole pieces of the electromagnet, okay, and see the Hall voltage. This is a way you again get back what is the magnetic field strength of the electromagnet. And routinely people do that. Now what we have done, we have now nanocomposite, okay, where these magnetic nanoparticles, nickel is embedded in SiO2. So we thought that is it possible to make a Hall sensor with this magnetic nanocomposite? Generally, people do not use magnetic nanocomposite for Hall sensing or magnetic field sensing. But what we have seen, the outer plane resistivity rho xy, when we vary the magnetic field, it exactly makes something which, you know, it is like BH loop or MH loop. So that means the resistivity depends on magnetization. Okay, there are a lot of theories in that. People have already established the theory for extraordinary Hall effect, which tells that there is a spin-dependent scattering. Okay, So generally in Hall effect, we do not talk about spin-dependent scattering. It is only the electron scattering in the material. But here it is spin-dependent because there are magnetic nanoparticles in that. That gives to a quite high, the Hall coefficient. Generally, we determine Hall coefficient in our experiment, and this is what we have demonstrated under a project of DST. And we also do routinely this measurement of our electromagnetic field sensing with this simple, very small sensor which we have made using nickel SiO2 nanocomposite. And this is a typical setup. And you can see as soon as we do this measurement, we get this loop. And from this loop, we determine Hall coefficient. So this was the first application which we have seen for this nanocomposite. Now, we know that we had started investigating a little further in magnetism. This is the second application I'm talking about. This is called tunneling magnetoresistance. Okay, what is tunneling magnetoresistance, which was proposed by almost independently by Professor Miyazaki of Tohoku University and Professor Jagdish Mudera from MIT. What they actually proposed in 1995, that if you have a ferromagnetic material and you have another ferromagnetic material or the same ferromagnetic material, and if you have a very thin insulating layer in between two ferromagnetic material, then you can see a good magnetoresistance. In fact, magnetoresistance was discovered, I think in 1987, okay, by Albert Fart and Peter Guenberg, who also received the Nobel Prize. They discovered it for very thin magnetic multilayer. But the idea of TMR was given by these two, where it is actually two magnetic layers, and in between there is an insulating layer. So it is because of the tunneling, we get a magnetoresistance, which is actually ratio between when the spins are at anti-parallel state minus when the spins are in parallel state divided by parallel. It depends on the polarization and also the density of state close to Fermi level. But there are a lot of applications which people immediately could discover after the discovery of TMR as well as the GMR. And you can see how the device application, there is a steady progress. And we know that initially it was long back which people knew about anisotropic magnetoresistance, and then the GMR, which came after the discovery of Albert Fart and Peter Guenberg, and 1995 TMR, which was discovered by Miyazaki and Mudera. And then you can see how these the memory devices have improved, and now we talk about MRAM, MRAM. Okay, these are very popular magnetic memory devices. So actually, I was very fortunate because I was traveling in 2011 and from one city of Europe to another city, and fortunately, Professor Mudera was sitting exactly beside me, and it was almost 2 hours of journey, and he gave me almost a lecture on TMR during his journey. So I got this idea from that discussion with Professor Mudera, and we thought that after coming back, that what actually Professor Mudera proposed, that you have a ferromagnetic material, another ferromagnetic, in between there is an insulating layer. So what we thought that our system is also almost similar. We have magnetic nanoparticles and in between silica matrix, very thin silica layer, as I have also shown you in this TEM image. So it is something like as if there are multiple these TMR, the combinations in one particular matrix. So we thought, let us do a MR measurement, and we did an MR measurement. And we found very good magnetoresistance in this material. Okay, and it happens only because of electron jumping from one material to another material through this one nanoparticle to another nanoparticle through this insulating layer, which Mitani had proposed long back in 1998. But we experimentally demonstrated that. And because of this quantum mechanical tunneling, spin up and spin down state electrons show different resistance, giving rise to magnetoresistance. So we also tried to find slightly more from what we had proposed in magnetoresistance. We started looking at, is it possible to generate something called exchange bias? Exchange bias is actually, it is important for magnetic storage device. Those who work in the magnetic storage device, they know that if we have a ferromagnetic layer and an antiferromagnetic layer, okay, so one can pin the state of spin of electron, and then we can observe a shifted loop in the magnetization curve. So again, we did some DFT calculation, and we found that when we take material to high temperature and quench it back during the elongation process, some of the spins, they actually flipped in the atomic site. So we have some electrons whose spins are aligned in one direction, some electrons which are aligned in the opposite direction. It creates something similar to ferromagnetic antiferromagnetic layer. And immediately we observe a shifted loop, which is exchange bias. And if you read this material, this paper, this is actually a review on what is the recent magnetic data storage, which is based on this ferromagnetic antiferromagnetic coupling. So some experimental demonstration we have added to the literature as an application. Now, these two applications I talked about, they are based on physics. Now I'll talk about one application which is based on physics as well as biology and some chemistry. So what is this application? This application is the detection of small biomolecule. So in order to detect small biomolecule, this is one technique which is nowadays used, is Raman spectrum. Raman spectrum, you know, it is many applications. One recent application is surface enhanced Raman spectroscopy. What is that? In case of Raman spectroscopy, we know that if we have an analyte and we shoot it with a laser, okay, so there are light which goes exactly with same frequency, that is Rayleigh scattering, and Raman scattered lines are with different frequencies. And if we do this Raman scattering for an analyte, we don't even see the signal. It is very weak signal. Okay, they are all biomolecule-based analyte. But if we place some nanoparticle now in that analyte, they are known as hotspot. Immediately there is an enhancement in the Raman signal. The reason behind this is that when there are metallic nanoparticle and then we shine laser light, what happened in the metallic nanoparticle, it creates something which we know from the basic physics, the plasmon. Okay, so plasmon means that the electrons which are conduction electron, and below that in a metal we have the positive ions. So it exactly oscillates like a simple harmonic oscillator, and if you quantize it, you create a plasmon. So these plasmon, actually they are known as hotspot. They actually concentrate the electromagnetic field very much. So when laser light falls on that, it concentrates light there and enhancing the signal by manyfold. Okay, so this gives a very high sensitivity to detect that biomolecule. So what we did, we again took this material which we have grown, this nanocomposite material. Here we just change the metal nanoparticle as well as the matrix. Here we use the gold metal nanoparticle because it is very good for optics application. Its surface plasmon resonance peak comes in the visible region. And we have a matrix silicon nitride, is similar to silicon oxide. Okay, so we grow it by plasma enhanced chemical vapor deposition, then by evaporation we coat gold, by annealing we create nanoparticle, and then we engineer the shape of this nanoparticle, and then we do a Raman measurement. So you can see there is a huge enhancement in the Raman signal. Almost we have calculated the enhancement factor, which is close to 10 to the power 8 to 10 to the power 9, because of very strong field. And what are the molecule we use? We use the rhodamine 6 molecule for detection. And then this is the Raman signal which we detect. So in order to understand that, we did FDGT simulation, and what we observed that for a particular size of the nanoparticle, the electric field is maximally enhanced surrounding this nanoparticle, which gives a maximum Raman signal, hence giving the detection of this molecule. And after that, we did work with even with E. coli bacteria, and we have demonstrated very recently that one can detect this E. coli bacteria with very high sensitivity. And then we also are doing a little further in that. If we put this nanoparticle instead of the insulating matrix on some organic framework, it can be used as magnetic resonance imaging contrast agent. And very recently in SCS Applied Biomaterial, it is published, the metal nanoparticle in the organic framework. So now this is the last application. It is again physics. And this application is to develop an electron source, particularly for electron microscopy and X-ray generation. Those who work with electron microscopy, they know this electron source is extremely important. But if we go back to our time when we were college students, we used to have this electron source, something like this. We know this electron source means there is a filament. You hit the filament, you get electron, and then your CRO and CRT and all these semiconductor devices, vacuum devices, we used to do experiment with this type of devices where the electron source was the field actually the thermionic electron source, and the theory was given by Professor Richardson, where it is shown that the thermionic current density depends on temperature and the work function of the metal. Almost at the same time, Professor Fowler and Professor Nordin gave another process of electron emission, which is called cold electron emission, where you don't have to heat any filament. You take a metal, electrons are filled up to Fermi level, you apply a bias, put it here on the cathode and place a metallic anode and apply a bias. Once you apply a bias, there is a little tinting of the energy barrier, and then electrons are actually tunneled, okay, by quantum mechanical process. All right. And then you can clearly see there is a variation of current density with electric field. So the electrons which are collected in the N. But you know this, it was discovered theoretically in 1928, 1930, but we had to wait many years because for that one needs nanomaterial. And the first work is started with this with nanotube. Now I will show you our very recent two materials which we have worked on and found that how to integrate it in a device. So this is the typical geometry of our electron source. So here we have cathode, where we have the material, that is whatever material you want. You discover a new material, put it here, okay, and this is the anode, and then you apply a bias, you record the current. You can also get an image. The image can be obtained if you change this cathode by some phosphor, or you coat this anode, sorry, with some phosphor material. Okay. So when this electron glows, they hit and you can get a image. I'll show you how this image is generated. So two nanohybrid material, which we have extensively worked on recently in this configuration, cathode anode configuration, gives very promising current density. This is a typical current density plot, and you can see for the MWCNT and neodymium oxide nanocomposite, which I had shown in the last part, we have a current density which is almost close to 20 milliampere per centimeter square. Almost, even to whatever the benchmark is there for device, it is even more than that. Okay, so all configurations are same. This is our technique, and here we show that how these electrons actually come out because by quantum mechanical tunneling process. All right. So you can see some field emission image also here. Now I show the few devices which we are making. So we had started our device development in the laboratory under a project of DST, which is known as Device Development Project. It is under Technology Translation and Innovation Division of DST. And we have made a field emission gun. India, we have given name in the field emission gun India. There are other laboratories also in abroad. People have made this field emission gun. And this field emission gun, here, it is completely cold field emission, cold electron source, where you can mount any material. If you discover tomorrow, you can mount it there, and you can put it in your electron microscope. There is a provision. Okay, so we are testing it for electron microscope, and this device was, I cannot describe much about the device, but in fact, it was one of the high impact research. It was considered for last 6 years at IIT Delhi, and also DST has given us is an excellent grade for this particular device development. Now, this is our dream project now. Now, once we have this electron source, this one application of electron source is microscopy, definitely this high resolution TEM, SEM, etc. But another application is X-ray generation. So those who work with X-ray generator, they know there is a big problem with X-ray generator in the present days, because the source you have to change, first of all. Second is you need chiller in order to cool it. And most of the time, the problem which people encountered with this X-ray system, X-ray diffraction system and other X-ray system, is with that source tube. So they have to replace it. So we thought, why not this cold electron source for X-ray generation also? Because what you need is a flow of electron. And then suppose you want to generate the X-ray of copper, say K alpha, K beta, you put it exactly in the X-ray generation source are, get a little bit slanted, and when electron strikes this metal, you generate this X-ray. Okay. So now it is under testing, and this is under the technology development program, again of Department of Science and Technology. However, we need to give a very high voltage, and we are, as it is the emission of X-ray, we are taking permission from BARC because it's a radiation. I'm just, this is very close to my heart. This is a device which I developed long back at Inter-University Accelerator Center. It's a large area position sensitive detector telescope. You can see that this detector is actually connected with a big vacuum chamber. So what is the importance of this detector? This detector is a very simple detector, particle detector, which consists of a gas ionization chamber that we generally study in our PG or UG course, and then a solid state detector at the back. So this is the structure. This is gas ionization chamber and this solid state detector. So this is gas ionization chamber, and below that, at the end, we have a solid state detector. So now what is the role of this particular detector? Those who work with different multi-layer or material with different elements, we always find a big problem to detect all the elements, okay, along with if there are very light elements like hydrogen present in your material, it is almost impossible to detect the elements as well as hydrogen. But if you couple this particular detector, okay, this large area position sensitive detector with a mass spectrometer, which is known as elastic recoil detection spectrometer, then one can get, you can see how nice spectrum one can generate for all the elements present in a particular sample, including hydrogen. So one can actually, tag this particular curve, and then you can project it in one dimension. You can identify the element, you can determine the areal concentration of the element, and you can also determine the atomic percent present in this element. So entire stoichiometry of the material can be determined using this. It is still used as a user facility. Many people use it at Inter-University Accelerator Center, those who work with multi-component material and multi-layer. So now I conclude this. What I've discussed is just gave an idea about what is the meaning of nanoscale material and how one can do synthesis and basic characterization of nanocomposite and nanohybrids, which are routinely done in our laboratory. And then I have discussed some applications and device development. In application, I discussed about Hall sensor, tunneling resistance and exchange bias, detection of biomolecules using surface enhanced Raman spectrometry, and then the last application was cold electron source and some devices I have shown. So I acknowledge the support from CSIR, DHT India, and that Germany, CFIPRA, and UMD Asia's been for all their financial support and many research equipment support. And for irradiation facility, I thank Inter-University Accelerator Center and also acknowledge two important facility of IIT Delhi, that is Nanoscale Research Facility, Central Research Facility. We are, my lab name is Nanostech Laboratory at IIT Delhi. If you visit sometime at IIT Delhi, please come to Nanostech Laboratory. We call it Nanostech Family at IIT Delhi. And thank you for your kind attention and if there is any question.
Thank you, sir.
And we can see a linear relationship between current and concentration. And base relationship is linear with R square 0.9.
Oh, I'm very sorry.
The
This
standard size of 30 volt
the
30 volt
audio
ammeter
is not clear. Can you please type the question in the chat box? I'm not getting the audio.
we can see P current and the figure we have drawn a plot between current and square, and we can see
Am I audible?
Oh, I'm so sorry. I am not even able to hear anything.
Okay. 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 Thank you, Santanu sir. Thank you for your nice
Yeah.
presentation.
Okay.
Sir, whether you are listening me?
Yeah. Now it is clear.
Yeah.
The previously
Ah,
somebody was
sir,
asking question. It
sir,
was not clear.
sir, it is a matter of great privilege to have you with us. It would have been much more better if you could have managed to be physically with us. But okay,
Yeah. Sorry.
it's not an issue. But next time. As you were busy, as you mentioned in your mail. So thank you once again, sir, for your nice presentation. And you are always a matter of inspiration for all of us. Thank you once again for your wonderful talk. And thank you and stay healthy, sir. Uh, we, on behalf of organizing committee, would like to offer sincere thanks and gratitude to you. Thank you, sir.
Thank you. Thanks to all of you again. And definitely next time I'll be there. Whether there is a conference or not, anyway, I'll visit you.
Yes,
We'll have some.
so we also see you in physically in our institution. All of
Yeah.
us,
Yes.
face-to-face interaction is more lively and more
It's true.
good. Yes. So
Yeah.
whenever, sir, you visit Agartala, you inform us.
Let
We'll
me.
get we'll small
Yes, we are.
gathering to any institution, any colleges, which is good
Yeah.
for every of
I would
us.
like to visit all.
Thank you, sir.
Thank you again. Yeah. So I unshared this and
Thank you, sir. Thank you.
we have also calculated the limit of
Shall we go for second our technical session? Dr. Subrata, can we start our technical session?
here are some of the
Yes,
relevant
yes, yes. You can start, sir.
Acha, is Navaparna is there? Navaparna? Hello? Is Navaparna is there? I think we have to wait for her for some time. Navaparna, are you there? Then how we can start with our presenter. I think someone's sharing his slide. Uh, so
No.
probably you
Hello.
can continue with
Okay,
your
sir. Okay, sir.
presentation. Ah.
Yes, sir. Yes, sir. Sir, now audible, sir? Now clearly?
Yes, yes, you are audible.
Good afternoon, sir.
It is on the title Study of Dynamics of Lunar Mass Ejection.
Hello. Shall I start, sir?
Yes, you can. You can.
Okay, okay, sir. Sir, namaskar, everyone, sir, and good afternoon. Good afternoon. And I am Rupavalli Talabatala. I am working. I am a research scholar in LPU in Department of Physics under guidance of Dr. Nabapanna Chakrabarti. I am working as a assistant professor of engineering college in Andhra, sir. Now, today we'll discuss my topic molecular interaction studies in glycolic acid, B vitamin systems through basic acoustic parameters. Now, second slide is that today we'll discuss about my introduction. Now, let me start my an introduction. First of all, acoustic. Acoustic means ultrasonic. Ultrasonic is the human. I mean, it is the waves of high frequency and human audible range 20 kilohertz and high directionality. And ultrasonic waves cannot move in vacuum. The wave constitutes high frequency shorter wavelength of a sound waves. These waves are travel at the same velocity in the sound, particular medium throughout the homogeneous as in sound and velocity remains constant. And then in nowadays, nowadays, in this ultrasonic technique is widely used in so many fields because this is the non-destructive technique. While doesn't any sample of, I mean, this technique is preferred. Why choose this technique means since it is does not cause damage in the sample while analyzing structure and shape and design doesn't cause any damage of in this samples. So that's why analyzing too easy, then we'll start the research then. And second thing is this is understanding the ultrasonic and thermodynamic properties of liquid mixtures is the crucially unreveal of intra and interstiticate of intermolecular interactions. And then so many applications are there in and there's so many fields and so many industries like textile industries, cosmetic and food and material science and medical industries, and so many industries are widely used in these those applications. So then after that, in today's presentations and my topic is using these acoustic and thermodynamic parameters on study on these chemicals. And first of all, the glycolic acid and niacin dipanthenol. And glycolic acid is the carboxylic group. This is mainly improve the moisture retention and antioxidant or anti-aging protections commonly used. And then second one, niacin and D-panthenol. Niacin and D-panthenol is the vitamin B family. So niacin is the vitamin B3 and D-panthenol is the D5. These all are essential for metabolism, growth and development. Organic substances are physiological functions. Then after that, this is my research methodology. First of all, now prepare the sample first, and then after inject the um, prepare the sample and injected the Antharpa DSA. In this corner of instrument is Antharpa DSA 5000 m. So injected injected a sample, and the samples are injected inside the equipment with the help of syringe injection. And these are two cells are measured in the density and speed of sound with method U-tube oscillating in this instrument. The U-tube, which is made from borosilicate glass, it is vibrate them frequency which vary to and simultaneously density and speed of sound are visible in the screen, sir. So then finally samples then injected the Antharpa DSA, they find the value of density and speed of sound of the samples at different concentrations and different temperatures. To finally the calculate the acoustic and thermodynamics of basic parameter of various molecular interactions in the samples. This is the this is the methodology for today's presentations. And then after that, the thermoacoustic basic parameters. What is the thermoacoustic parameters? So many they are using these all are basic parameter of thermoacoustics. First one, acoustic impedance, adiabatic compressibility, and Vada constant, Raoult's constant, and intermolecular free length, and Van der Waals constant. Now, one by one, we'll discuss. And then after that, these are resultant discussions. And acoustic impedance Z is equal to rho into S, adiabatic compressibility beta is equal to 1 by rho into S square, and Vada's constant W is equal to beta power 1 by 7 by m by rho, and Raoult's constant S power 1 by 3 by m by rho, and intermolecular free length and van der Waals equations. One by one, these are in figure 1, figure 2. First of all, acoustic impedance. The volume of the solution decreases in the concentration rises because the more particles and acoustic impedance particles are present in. As concentration rises, acoustic impedance rises in the as shown in the figure 1. In this figure, mm, and then this demonstrated the strong molecular interactions between the mixture constituents. The increasing of acoustic impedance include the stronger intermolecular interaction and closer molecular packing, conforming the enhanced solute solvent interaction within the system. In this figure is acoustic impedance and niacin 0.01 with glycolic acid, and 0.02 0.03 glycolic acid, and same like dipanthenol 0.01 0.02 0.03, and different concentrations and different temperatures in aqueous glycolic acids. And then figure 2 is indicating, and this is the adiabatic compressibility. The compressibility is the solute molecular decreases as a result in the accumulated of the solvent molecules around them as shown in the figure 2. The observed decrease in compressibility suggests medium becomes less compressible and more rigid due to the strong molecular interaction and structural organizations. The adiabatic same like in acoustic impedance, same the different concentration of different temperatures in aqueous glycolic acids. And figure 3 is indicating the Vada's constant, and the density is decreases increasing in temperature, but while the glycolic acid is the concentration vitamin B, niacin or dipanthenol, molality rises. So does density, Vada's constant goes up as focus goes up and increasing. And this strongly display the solute and solvent interaction, water solution in as showing figure. And the rises of Vada constant indicate the stronger intermolecular bonding and provide insight into the relationship between the compressibility and molecular structure also. And then Rao's constant. In this, as the concentration is rises, Rao's constant as usual increases. Because of in this densely packed system, the number of component grows, leading to an increasing in the interaction as shown in figure 4. And then intermolecular free length. Intermolecular free length, same like concentration increases and then unrestricted length is decreases. The intermolecular cohesive, the greater, which is makes a molecular stick together more strongly. The sound velocity in the mixture increases as the free length decreases regularly, as shown in the figure 5. And then last one, van der Waals constant. The figure 6 is demonstrates how van der Waals constants decline in the concentration with concentration when glycolic acid changes from the solid into the liquid, and the binding interactions in the solvent and solutions dimensions. The decreasing of free length signifies our molecules are coming closer together, indicating the increased cohesive and stronger attractive forces between the molecules. So, as shown in the figure 6, is indicating the van der Waals constants decline with the concentration. And now and after that, in this future scope of this study in this slide, and the exploring and first of all developing the new theories and models to better understand the behavior of various substances in the solution, and applying the knowledge gained to develop optimized drug and product formulations in the various industries, and then inspiring the future research on thermodynamic properties and so many organic compounds, so many already so many organic compounds are have done the completed thermodynamic and acoustic parameters. Now so many organic compounds not present in the thermodynamics and acoustic parameters, so inspiring the future research on thermodynamic properties and then with other organic compounds in the solutions, exploring the use of different solvents and solutes and their study in thermodynamic properties. These are now, last but least, the conclusion will in this my presentation. This study examines the acoustic and thermodynamic properties of glycolic acid and with water, niacin, and deep ethanol system at different temperatures using ultrasonic measurement at 3 megahertz. And each parameter, in this significance of this study, each parameter consists of acoustic properties of represents specific physical interactions important for understanding molecular behavior in the solutions. And then one by one already discussed above, and the increases of acoustic impedance indicating the stronger intermolecular interaction and the closer molecular packing and confirming the enhanced solution solvent interaction in the system, liquid system. And then compressibility decreases, such as the medium becomes less compressible. And then finally, free length is decreases, molecules are coming closer together, indicating the increased cohesive, strong attractive forces between the molecules. And then Rao's constant increases, enhance the molecular associations, interaction strength contribute higher molar sound velocity of the solutions, and Vada's constant rises and strong molecular bonding provides insight into the relationship between the compressibility and molecular structure. And same like van der Waals decreases and reduce the effective molecular volumes and possible weakening the structural rigidity and indicating the change molecular arrangement and interaction space. This is the finally conclusion, sir. These all are using this in my today's presentation in my research. I mean research study. So many references are there in these all are references are using in this presentation. Thank you so much, sir.
Thank you, Rupavalli. Um, any question from the audience side? Is there any question from audience side? Anyone want to ask anything about Rupavalli? Want to know about from Rupavalli?
Uh,
If, if okay, thank you, Rupavalli.
Thank you so much, sir.
Someone is. No, wait a minute, please. Let our two presenters are there. They are also waiting from time. So please wait for our call. Please don't join. We will call you one after another. So next, Dr. Suman Odhikari is there. Dr. Suman.
Yes, sir.
Okay. Dr. Suman, how are you?
Fine, sir. Fine. How are you, sir?
And yes, fine. He is. See, Pradeep also here.
Dr. Devnath is also present.
Dr. Devnath is there.
Actually, I was supposed to come,
You are
but
waiting for you.
yeah, actually, I was supposed to come because of some urgent work, I could not come.
Okay, okay. So basically, we are. I think you have some duty also. Acha, Navavarna is there, na? Acha, Navavarna, wait for some time. Let Odhikari to finish, then you start. Okay, Navavarna. Hello, hello,
Yes, sir.
Navavarna.
Yes, sir. It's completely fine, sir.
Okay, you wait. Let Dr.
Yes, sir.
Odhikari to present, and then you continue. Huh? Okay, Dr.
Okay.
Odhikari, please
Okay.
continue. Let me introduce our today's speaker, Dr. Suman Odhikari. We are calling for some time. So, Dr. Odhikari is an associate professor in the Department of Chemistry at Government Degree College, Dharmanagar, with about 18 years of teaching and 8 years of administrative experience. His research interest in supramolecular and scholarship, if I say wrong, protected. He has also completed multiple institution minutes, another 5 minutes for discussion.
Sir, shall I start?
Yes, 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 you continue.
Actually, sir, what happened? This Rupabali madam, she is presenting. She needs to close this thing so that I can present.
Only, please close the presentation.
Hello, sir. Am I audible?
Yes, Dr. Odhikari.
Yes, sir. Sir, am I audible?
Yes, 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 you are audible.
Sir, shall I start my presentation?
Your slide is also visible.
Yeah. Okay, sir. So first of all, I would like to express my sincere gratitude to the organizing committee for giving me opportunity to deliver my presentation. And I would also like to express my Sincere thanks to Dr. Bomik for inviting me. The topic of my presentation is unveiling supramolecular network engineered via tetranyl and hydrogen bonding interaction in PB2 complexes. So before going to the main presentation, first of all, I would like to discuss briefly about what is supramolecular chemistry. The supramolecular chemistry, it is known as the chemistry beyond the molecules, and it started in 1967 when its pioneer father, Professor Pedersen, he discovered crown ether, and he found that in the cavity of the crown ether, it can trap certain ions like potassium ion by non-covalent interactions. And after that, Nobel laureate Cram, he also synthesized krypton. He found that it can also trap the potassium or other alkali metals ions. And at that time, it was known as host-guest chemistry. The term supramolecular chemistry was introduced by Nobel laureate Land. He said that it is a chemistry beyond the molecules or chemistry of the non-covalent interactions. Actually, when atoms are joined together by covalent interactions, it forms molecules. And when molecules are interacted by the non-covalent interaction, it forms the supramolecules. And supramolecular interactions, mainly the non-covalent interactions like hydrogen bonding, hydrophobic, hydrophilic, this type of interaction plays the important role for the association of the supramolecules. In the natural system, we also found that the supramolecular interaction exists in case of the DNA, where adenine, thymine, cytosine, guanine are held together by the hydrogen bonding interactions. And supramolecular chemists are always looking for the discovery of new type of interaction. Among this new type of interaction, one important is the sigma hole interactions. And this is known as a sigma hole interaction because it happens by the elongation of the sigma bond. And in the sigma hole interaction, the metals which are interacted with the Lewis base. In the case of the group 14 element, when the sigma hole interaction is observed, it is known as the tetranyl bonding. In case of the group 15, it is known as nictogen bonding. 17, it is known as chalcogen bonding. In the group halogen, it is known as a halogen bonding. The tetranyl bonding exists in the group 14 elements, where the lead, carbon, silicon, germanium, they are interact with the nucleophile or this Lewis base. And we are particularly interested about these tetranyl bonding interactions. And this tetranyl bonding interaction, it was discovered not so far ago, just in 2013, when the Professor Frontera, he observed this tetranyl bonding interaction in this. This is the first publication in the NGUChem in 2013. And this tetranyl bonding interaction play a very important role in the drug design, even in the enzyme catalysis. And recently, it was also found that this, in case of the protein ligand interactions or in the drug discovery, the tetranyl bonding interaction play a very important role. Acetylcholine, which is a neurotransmitter, which are in which when it interacts with the ligand, there is a tetranyl bonding interaction, and which actually facilitates the drug delivery. So in the drug design, in the enzyme catalysis, or in the molecular recognition process, this tetranyl bonding interaction play a very important role. So we are particularly interested about lead, because although lead is a toxic element, but it is a model system to study the tetranyl bonding interaction, because lead shows the coordination number from 2 to 8, and it can form diverse supramolecular network. When the coordination number is more than 6, lead actually forms the hollow-directed complex, and when the coordination number is 5 or below than 5, it is formed as hemi-directed complex. And in all these complexes, this lone pair of electron in the 6s2 remain inert. And for the synthesis of the this lead supramolecular network, which are engineered by the tetranyl bonding interaction, we use simple this isonicotinium hydrogen ligand. This ligand can actually exist in the ketoenol tautomerism. And you can see in the ligand structure, there is a pocket where this one pyridine nitrogen, one this azomethane nitrogen, and this oxygen, they form a pocket where it can bind the metal ion. And we have used different lead salt, lead nitrate, lead iodide, lead thiocyanate, lead chlorate to synthesize these 4 complexes. And we found that this complex 3A and 3B IR is almost similar. So we predicted that although we use a different procedure, but that the complex is same. And after that, we also checked the 1H NMR, and we found that this 3A, 3B NMR spectral pattern is also same. For checking the phase purity of the complex, we took the powder XRD, and powder XRD exactly matched with the CIF of the solid state structure, so which indicates that in the bulk phase also this complex is pure. And we after that we took the single crystal analysis, and this is the camera structure of the single crystal analysis. Although you can see in all these three complexes we used different lead salt, and this anion, this counter anion also involved in the supramolecular network, and this supramolecular network is stabilized by the covalent bond introduction as well as this tetratyl bonding introduction. And this is the solid state structure. As you can see in this structure, there are coordinate bond PBN, PBO, PBI, PBS, but apart from that, there is PB or tetratyl bonding introduction and PBC tetratyl bonding introductions. And this supramolecular network also stabilized by the pi-pi introductions and also by the hydrogen bonding and this tetratyl bonding introductions. After that, we also calculate the energy associated with this complex, and we found that in the DFT calculation also, these tetratyl bonding introductions, hydrogen bonding introductions, and the pi-pi introductions stabilize the supramolecular architectures. And recently also we published this work in this inorganic chemistry communications, and from that we can draw the conclusion that tetratyl bonding introductions play the vital force for the generation of the supramolecular network. And in the case of the complex 1 and 2, the ligand remains actually neutral. But in the case of the complex 3, actually it gets deprotonated, and pi-pi introductions and other this hydrogen bond introductions stabilize the supramolecular network. We also tried to explore the tetratyl bonding introduction in the aliphatic systems. All the tetratyl bonding introductions till published, all systems explored in the aromatic system, mainly the pyridine systems. And we tried to explore this using the simple polyamine and this our 1,1 dicyano-2,2 diethylene ligand. And for that purpose, we used lead dicyamide salt. Actually, I want to share one interesting thing with you. We have tried several lead salts to form the complex, but we found that this lead chloride, lead chlorate, lead thiocyanate, lead iodide do not form actually complex, or we did not get any single crystal. But when we use the lead dicyamide salt we actually synthesize in a lab from the sodium cyanide and the lead salt. And we found that when we treated with this aliphatic ligand, it immediately formed complexes. And we checked the IR. This you can see this CN peak is visible, which actually indicate that the coordination of this 1,1 dicyano and 2,2 diethylate ligand. And we checked the solid state structure by X-ray crystallography, and we found that in the case of the complex 1, it is actually neutral chelate. And here in the solid state structure, it forms a dimer by tetratyl bonding introductions. And these are the supramolecular network, which is stabilized by the hydrogen bonding introductions, and also there are tetratyl bonding introductions. Since this is a aliphatic system, so there is no existence of the pi-pi introduction, and it forms a 2D ribbon-like structures. In the case of the complex 2, which is a co-crystalline aggregate of the 2 lead tetraene and 2 cationic part and 2 anionic part, and the energy associated of this structure is very high, because since here there is an ion pair introduction exists. And these are the solid state structure where you can see there is a tetratyl bonding introduction also exists in the solid state structures. And these are the 3D supramolecular stacked column where this hydrogen bonding, tetratyl bonding introduction plays the vital force for the generation of this supramolecular network. And we have also calculated the energy associated with both this structure. In case of the complex 1, it is minus 45.5 kilocalorie, which is actually standard system. If you check in the literature, where there is a tetratyl bonding introduction, this type of energy 40 to 50 kilocalorie per mole associated with the network. But surprisingly, in the case of the complex 2, the energy is very high. And because it is a existence of the 2 cationic part and 2 anionic part, this hydrogen bonding introductions, tetratyl bonding introductions, and the ion pair introductions stabilize this, and there is and because of this, it shows very high energy. And we also use Hartsfield surface analysis to validate the tetratyl bonding interactions, where we can see there is a PBS, PBN type of tetratyl bonding interactions exist in the solid state structures. And this is the Hartsfield 2D fingerprint, where we explored different type of introductions and the percentage of interaction present in the molecule. So actually, by using this simple polyamine ligand and this 1,1 dicyano ligand, we explored this tetratyl bonding in the lead complexes by using the simple aliphatic system. And this was the actually first report where aliphatic systems are used for the exploration of the tetratyl bonding interactions. And this is published in the Crystal Growth and Design recently. And recently we have also explored the tetratyl bonding interactions in the thious semicarbazone system, although it is not published yet, so I am not going to discuss. Although tetratyl bonding interaction discovered very recently, but it plays very important role in the stabilization of the supramolecular network. Not only tetratyl bonding interactions, we are also recently exploring the spodium bonding interactions. Spodium bonding interactions presents in the case of the group 10. And recently, this supramolecular chemists they are exploring different type of this new type of non-covalent interaction, which actually exist in the different type of supramolecular network. And I would also like to thank Professor Antonio Frontera, who discovered this tetratyl bond, and he actually we are doing collaboration work with him, and he by using DFT calculation he calculated the energy associated with this systems, and Professor Raymond Bouchard for single crystal analysis, Professor Warner Kaminsky also for single crystal analysis. Thank you all. If you have any question, any query, you can ask, please. Dr. Devnath, if you have any question. And Dr. Rahul Bhattacharya, if you have any question. Madam, if you have any question, please.
Wait.
Thank you, Shimon. Your nice presentation.
Thank you, madam. Thank you.
And physically you present.
Yes,
Next time.
actually, I told madam that I shall come, but because of some urgent work, I could not come. Sir, if you have any question, please.
Shimon, next time we
Yes,
have
sir.
less. We have so many participants in quiz.
Yes.
Yeah, so next time we'll.
Now,
Dr. Devnath, your mic is off.
Navaparna is there? Navaparna.
Hello?
Navaparna, are you there?
Yes,
Yes.
sir.
Navaparna.
Yes, sir.
Wait a minute. So
Sure.
now our next presenter is Navaparna Chakraborty. We are she our next invited speaker. Let me introduce Navaparna with all the audience. Dr. Navaparna Chakraborty completed his PhD in applied physics in 2021. Dr. Chakraborty is associated with Central Instrumentation Facility at Lovely Professional University. Dr. Chakraborty's research interests into thermophysical and acoustic properties of liquid mixture, molecular interaction studies, and green corrosion inhibition. She has authorized multiple research articles in reputed review journals. Her H index is 16. So I request Dr. Chakraborty to continue his lecture, and your time is for 20 minutes. maybe 15 minutes also. You can complete. And because of so many, we have started late, and also people are waiting for in the queue. So
Yes.
now, Madam, please start.
Thank you so much, sir, for this lovely introduction. I want to express my gratitude to Shubhrata sir for giving me this opportunity. Thank you so much, sir, and thank you, everyone. Very pleased to see everyone. Rahul sir, and I think Samhita ma'am is also there. Hello, ma'am. So, moving on, let me add my PPT.
Yes,
Sir, is it visible?
yes, 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 it is good.
Okay. So, okay, good afternoon, everyone. So, today I'll be giving my talk on exploring nanoscale, fundamental, and applications of electron microscopy. So these are the contents which I'll be covering throughout my presentation, which involves a brief introduction of microscopy, then types of microscopy, history of electron microscopy, types of electron microscopy, and mainly I'll be talking about field emission scanning electron microscope, along with energy dispersive spectroscopy, their requirement for sample preparation, advantages of FSM, applications of FSM, a brief discussion about nanotechnology, their applications and examples. And at the end, I'd like to introduce about CIF. So this is the content. So we visually understand the world, interpreting the shapes, colors, pattern through the remarkable capabilities of our eyes. However, this perception is limited to what lies within the range of human vision, leaving an entire universe of microscopic details hidden beyond our natural sight. So, to explore these unseen dimensions, we rely on powerful tools that extend our vision, bringing into focus the intricate structures and phenomena that define the microscopic world. So, as it is said, the microscope reveals worlds within worlds hidden beyond the limits of human sight. So, the microscope is not just a tool, but a gateway to understand the fundamental building blocks. So there are mainly two types of microscopy: optical microscopy or light microscopy, and electron microscopy. So all of us are aware about light microscopy. So light microscopy utilizes visible light to generate images, and the magnification range from 42,000 with the resolution limit about zero point 0.2 nanometer. But as we were moving towards more intricate details, it was necessary to understand the materials at a very core level, at a very fundamental level. So in order to understand that, sorry, my camera was off. So in order to understand that, electron microscopy was invented. So electron microscopy, as the name is indicating, it uses highly energetic electron beam to generate images, thus increasing its magnification from 10,000 to 10 lakh, and resolution limit up to 0.5 nanometer, making it very best for ultrastructure of cells, viruses, nanoparticles at atomic level. So electron microscopy was first invented by Ernest Ruska and Max Knoll in 1931, for which they got Nobel Prize also in 1986. So there are mainly five types of electron microscopes: transmission electron microscope, scanning electron microscope, scanning transmission electron microscope, environmental scanning electron microscope, and reflection electron microscope. So transmission electron microscopes works on the principle of transmission of those highly energetic electron beams throughout very thin specimen, thus which produces 2D images. And as it is works on the principle of transmitting those highly energetic electron beams, the image which we get is a very highly resoluted images, thus making it very useful in order to analyze viruses and cell structures. As you can see in my presentation, I have attached some images also, images generated from TEM. There you can see a nerve, peripheral nerve. You can see an image of cilia, some tissue also you can see. These all have been generated from TEM. The next electron microscope is scanning electron microscope. So this works on the principle of scanning the specimen, the surface of the specimen through those highly energetic electron beams, and thus producing 3D images. As it is producing 3D images, although these images are having lower resolution than TEM, but they are having better depth of field, which makes it best for analyzing the surface morphology of any sort of materials, maybe biological samples and so on. I have also attached images from SEM also. You can see a micrograph of selenium respiring bacteria. You can see a micrograph of porous polymeric foam, and you can see gold nanoparticles. And the interesting part is, as I'm working with FSM, all these three samples I have analyzed myself. So all these three samples I have seen that how do you really have to prepare them. So the basic knowledge, the application knowledge also comes within it. Now, the next electron microscope is scanning transmission electron microscope. Now, this combines the working principle of both SEM and TEM. So, it simultaneously scans the surface of the image as well as transmit the highly energetic electron beam throughout the whole specimen, thus generating highly resoluted images along with the depth, which was the limitation in the SEM, thus making it best for analyzing nanomaterials and for elemental analysis. Here also I have attached 3 images of STEM. Now, moving on, our fourth type of electron microscope is environmental scanning electron microscope. Now, it is a special type of electron microscope. What it does not require any sort of vacuum, which was a special criteria for SEM, TEM, and STEM. And in this case, it is not required, and it works within a gaseous medium. So if you're working with any sort of wet material or any hydrated samples in which you know that yes, there will be moisture in that, so in those kind of samples, you can easily use environmental scanning electron microscope. Here you can see I have attached some images also. You can see the images of water droplet on hairs. So obviously they are hydrated sample, so you can take images of those samples also. Along with it, you can see there is a eukaryotic cell also, and fungus spores tuck inside a leaf. You can see that how clear that image is. We can generate it with ESM. Now, the fifth type of electron microscope is reflection electron microscope. Now, what it does, it focuses highly energetic electron beams onto the specimen at a certain glance, at a certain angle. Now, due to that angle, the reflected electrons from those, after interacting with the samples, get collected by the detector. Now, due to this reflection of this electron, whatever image is being generated, we can get from reflection electron microscope. Now, you can see I've also attached the micrographs of some REM images. Now, due to this property, it is very much useful in order to understand the surface of the structure, that what kind of structure it is having. You can see that there is an image for electron diffraction pattern also. Some crystal surfaces of silicon, platinum, gold, and silver also. So this is very much useful for surface analysis in order to understand the surface structure. Now, the main electron microscope which I'll be focusing on is field emission scanning electron microscope. It is a special type of scanning electron microscope, and I'm saying it is special because it uses field emission gun as an emitter in order to generate these highly energetic electron beams which interact with your sample, and thus giving us highly resolution images at nanoscale. And as it is having features of low and high voltages, it can be very nicely used for biological samples also. Now, as you can see, there is in-lens Schottky field emission gun attached to it, through which the highly energetic electron beams are being generated. Now, this is from thermal field emission gun, and here we are having Schottky field emission gun. Now, the field emission gun produces the electronic beam, highly energetic electron beam. It can reach up to 1 kilovolt to 30 kilovolt, means 30,000 volt it can reach up to. Now, the main principle involves the working of FSM is that highly energetic electron beams are generated from the emitter. Now, these high voltage beams are allowed to pass through some apertures, which are electromagnetic lenses, in order to focus and to redirect them. Now, after passing through these apertures, they get bombarded on the specimen, and after interaction of these energetic electron beams with the sample gives us the morphology. Now, the main construction involves an electron gun, electromagnetic lenses, scan coils, detectors, specimen chamber, and a computer in which you can visualize whatever morphology it is. Now, there are mainly two types of gun, thermoionic emission and field emission gun. Now, here lies the difference between SEM and FSM. In SEM, thermoionic emission gun was used, and in FSM, field emission gun is used. Thermoionic emission used a tungsten filament through which onto which through thermoionic emission electron beams were used to be generated. Now, this was prone to get heating very easily, and as the tungsten filament was used, the surface area analysis was quite large. Now, this limitation was overcome at FSM, which uses a field emission gun, in which the material is bombarded with strong electronic fields, due to which electrons are being generated. Now, at the tip of the tungsten filament, there is a zirconium tip used, which makes it very narrow, due to which the beam which is being generated, that is also narrow. Now, at the later end, there are electromagnetic lenses which are having condenser lens as well as objective lens. Now, what condenser lens do? The electronic beam generated from the filament comes through the condenser lens. Now, condenser lens reduces the diameter of that electron beam so that it can be easily focused onto the specimen. Now, objective lens, what it does, it focuses that electron beam. Now, then it passes through scanning coils. As it is scanning electron microscope, scanning coils are used to make those electron beams scan over the entire region of the specimen, so that the entire region is exposed to those highly energetic electron beams. Now, after these interactions, all these electrons are being are analyzed by the detectors. So there are mainly three types of detectors: secondary electron detectors, backscatter detectors, and X-ray detectors. As you can see in the image, that how they are attached correspond to each other. Now we'll discuss about this detector in the later slides. Now, the specimen chamber. In the specimen chamber, our specimen is, or the sample is mounted. Now, the specimen chamber should always be in a vacuum stage. It is necessary because obviously we are analyzing the sample at nanoscale. So even if there is a small dust particle onto your sample, you'll be getting misleading results. And obviously it might hamper with your sample also. So all the analysis inside the specimen chamber is done under evacuated state, under vacuum state. Now, this vacuum can be achieved with the help of purging nitrogen also. Now, the main working involves, as I mentioned before, through electron gun. You can see through the electron gun, electron beaming is generated. Condenser lenses are there, which reduces the diameter of the electron beam. And these electron beam then passes through the scanning coil, which makes them scan the entire area of the specimen. And objective lens is used to focus, because obviously, as like an optical lens, objective lens is also used to focus that image. And after those interactions, the detectors detect or collect those electrons from the specimen and gives us the image. Now, what is exactly happening when I'm saying that the energetic electron beams are interacting with your samples? When these highly energetic electron beams are interacting, which means they're interacting with those elements also present in that sample, which is comprising that whole sample. Now, as it is imparting its energy to those elements, the electrons from the outermost shell, obviously after gaining some electron, will move out from the outermost shell of the electron. Similarly, some electron might not just interact with the sample, but also come near the nuclei also. Okay, so in both the cases, secondary electrons will be emitted, backscattered electrons will be emitted. Along with this, a characteristics X-ray is also emitted. So all these electrons are being detected by different detectors: secondary electron detectors, backscatter detectors, and X-ray detectors. Now, what is happening in secondary electron? How that is able to reveal the morphology? As I mentioned before, that as the energetic electron beams are interacting with your sample, they are knocking out the electrons from the outermost shell. Now, how this electron is coming out of that atom, at what energy, at what velocity, at what angle, this all reveal the morphology of that particular sample. Backscattered, on the other hand, not actually knock out of an electron, rather it comes near the nucleus, but as due to repulsion, it moves away from it. Okay, and due to this moving away, as different atom are having different atomic number, depending upon the scattering, it reveals that what kind of morphology or what kind of elements are present in that particular sample. So in this way, backscatter electrons reveal a different information. And as I mentioned before, that characteristics X-rays are also emitted. So these reveal about the elemental composition, like what kind of elements are present, at what percentage they are present, and how they are distributed. We'll discuss it in our later on slides. Now here I have attached some images, the same image taken from secondary electron detector and backscattered electron detector. As you can see, the secondary electron detector image is a little bit dark as compared to the backscattered one, because backscattered, as the atomic number increases, the scattering increases, and due to the scattering, the brightness increases. So in short, you can say as the atomic number increases, the brightness of the image increases. As if you are taking it with a backscattered detector, you'll get far more bright image than that. Now the next one is energy dispersive spectroscopy. Now this is an external attachment to FSM which allows us to measure
Hello. Over now.
Yes, sir. Am I audible, sir?
Yes, yes. Take another 5 minutes, please. Hello. Over now.
Shall I
Over
continue,
now.
sir?
Yes, yes, yes.
Shall I?
Continue. Another 5 minutes.
Oh,
Yes. Continue.
okay. Okay. So with the help of EDS, we can determine the elemental composition of the specimen. But it is also having some limitations like helium, hydrogen, lithium we cannot detect, because the peak which we get through EDS is quite, they overlap over each other. So the principle I have already discussed. Yes, this is the spectroscopy and the image which we get from EDS. You can see there is some spectroscopy graph, and along with it you can see the weight distribution, atomic distribution. As I mentioned, that EDS not only reveal the qualitative analysis, that what kind of element presents, it also reveals the quantitative analysis, that what kind of elements are present, along with it what percentage they are present, atomic and weight percentage. And it is equipped with mapping also. In mapping you can see that how those elements are distributed throughout the sample. Now this is very important from the pharmaceutical point of view, from electronic point of view, from material characterization, from lithography, and so on. Now, as electron microscopy reveals this type of intricate and fundamental detail, the sample preparation of these kind of tools are also quite complicated. So the first and foremost necessity condition is that your sample should be completely dry in nature, and your sample should be conducting in nature. But obviously if you are analyzing any biological sample, that is not conducting in nature. So in order to make it conducting, we use a gold sputter coater, which creates a very thin layer of gold onto the surface of your sample, which makes it conducting in nature. Now why the conducting is necessary? Because through the conducting only, the highly energetic electron beam will interact throughout the sample. Otherwise you will be observing charging effect, where will be there will be an accumulation of charges at a certain place, and rest of the part will be dark. So you'll be getting an uneven, highly contrast image, which will not be beneficial, which will not be revealing, or which will not be giving you proper data. So this is the workflow of biological sample preparation. I'll not bore you through it. for cellular tissues, for bacteria. Now, the advantages of FSM, obviously higher resolution, nanoscale imaging with finer details, excellent surface detail, morphology, clear images you can get with high magnifications. You can see I have attached two images of bacteria, lactobacillus I have attached, and on the bacteria you can see how clear it is, and see the magnification is up to 7,000, 1 micrometer, and how clear it is.
2 minutes, no wonder.
Yes. I'll just wrap it up. Few figures just I have to show. So the applications, it is majorly used for the material characterization, nanotechnology, topographical and morphological composition data. These three images which I have attached over here, these I have analyzed by myself. Now these are few of the images which we have taken from FSM, AFM, cantilever. AFM, yes, this is another type of microscope, atomic force microscope. I will discuss on some other day. This is one another image of gecko. This was also generated from FSM Geol. Glass fibers, a mesoporous silica, nanofibers, zinc nanopowders, carbon nanotubes, a microvilli cross-sectional view. So, brief introduction. I'll conclude it with the brief introduction of nanotechnology. As we are all aware about nanotechnology, it relates to the field of technology dealing with the particles ranging from 1 nanometer to 100 nanometer, because these particles shows very different behavior, different characteristics at nanoscale level rather than as they're in the bulk level. So, which makes their wide application in various arena. So, as Feynman has said, the principles of physics, as far as I can see, do not speak against the possibility of maneuvering things from atom to atom. These are the few applications of nanotechnology, a few references which I have gone through. At the end, I'll just like to aware you all about the central instrumentation facility. As sir I've mentioned, I'm working in it. I'm the lab in charge of field emission scanning electron microscope along with the spectroscopic instruments. So we are having these all instruments in our central instrumentation facilities, and we are open for characterization and collaboration. So and this is the upcoming event in the month of June and July. There is a summer training for all the instruments mentioned over here. So this is the email ID and website. If you have any query regarding sample or anything, you can contact me also. So thank you, everyone. Thank you for this wonderful opportunity.
Thank you, Navaparna. You have covered all these equipments, which are modern equipments today's world, and I think all the facilities are available in your center under your
Yes, sir.
supervision.
Yes, sir. Yes,
So
sir.
it's good for the who are listener in this seminar. They can easily contact you for any further characterization and others. I think so. No?
Yes, sir.
So these facilities, as all facilities are in a single hand, so you can provide help the people taking the data and other. So basically,
Yes, sir.
Navavarna is an alumni of Women's College. So we
Yes,
are
sir.
happy that you are in a certain positions is there. So we are
Thank
proud
you
of
so much.
that Navavarna is in there. And if any question from any audience, please unmute yourself. We are with we'll 1 minute or 2 minutes for discussion. So anyone have any queries, please continue. So if no further question, then I again thanks Navaparna. And our next speaker is Devanjan Sen.
Thank you so much, sir.
So I request Dr. Pradeep Devnath introduce our next speaker, who is invited lecturers.
Okay.
Audible, audible.
Okay, our next. Okay, computational chemist. He earned his PhD from Jadavpur University.
The mute, please. The mute. Yes, I think now is okay. It's okay. It's okay.
He earned his PhD from করছো তোমার এটা মিউট করতে হবে ভালো হবে না our next Our next speaker is Devanjan Sen. Dr. Devanjan Sen is former academician and computational chemist. He earned his PhD from Jadavpur University. Presently, he is and he has successfully published over 50 research articles in reputed international journals. He is also author of 4 book chapters. His research focus on the design and development of efficient synthetic routes and molecular scaffolds supported by the mechanistic validation using in silico structures based and the rational drug design approach. He has hold 2 Indian patents and so on. With this short CV, I request Dr. Devanjan Sen to present his research paper, and the platform is over the Dr. Devanjan Sen. Dr. Sen, please.
Thank you, Pradeep sir, for your kind introduction. Am I audible?
Yeah, you are audible.
Yes, sir. Yes, so I'm going to, because there is a lack of time and just straightforward, I'm coming to my presentation.
Yes, sir, your time is 20
Um,
minutes, sir. Sir, please confine in time because you are late, behind the time. Okay, sir. Thank you. Yes.
Hello? Am I audible and my screen is
Yeah,
visible?
yes, everything is okay. You can start, sir.
Okay. Okay. Because exploring machine learning and deep learning for the designing of bioactive small molecules. So it is a very vast field and very briefly and concisely I just highlighted, and in some other in depth. So first of all, why ML and machine learning matters today everywhere, in Google search to Netflix to drug discovery, in diagnosis, or in literature search, everywhere using AI and ML. But I feel personally using AI tool is not a skill. So the why using AI tool is not a skill. We'll try to address this line, and we have to learn first what is AI and ML. And in this time, time, I will explain these things a bit briefly. So when we see some traditional program, suppose we have x1, x2, we will get y value. That is 2 plus 3 is equal to 5. In the program, we define a relation with the addition function. But in AI or ML, we'll give the input, and from the input, the machine will what will be the output. Okay, so it use algorithm. Using the algorithm, it will find the relationship between the x dependent variable and independent variable. Okay, this is the basic difference between AI and ML. Now, as a pharmaceutical chemist or technologist, our focus is on drug discovery process. how we can find new drugs. We know discovery drug is a long process. It takes 14 years. So this AI, ML, and all the things I'm going to discuss is lie in the part of exploratory research. Now, one question comes in our mind: what is AI? Is it a software or what it is? We will find in our next slide. And thus, AI really works and it has the capability to discover new drug molecule. Answer is yes, if you train it properly. Else, if you open the Google Gemini and if you issue a prompt that generate the image of generate the image of the resonance structure of 1,2-diazine, you will find it will give a mess. Maximum time it will generate the structure of 1,2. It will do what if you give this to Google Gemini and ChatGPT horrible. So if we search the literature, we will find, yeah, it can generate. These are the examples. I'm not going in depth. And this is another example that is AI designed drug. It takes only 3 months to discover a new molecule. A new antibiotic, helicin, is identified by the AI. So I'm not going in depth in this slide. So we have a number of tools like DrugX, PyRM. These tools significantly help us to design a new molecule. Then why we learn and so we have lots of techniques like VAE, RNN, transformers, and diffusion models. Ultimately, these models are available on GitHub, so you could download it, use it. But why? Because if my data set doesn't align with the pre-trained models, then we'll end up with wrong result. So initially, we used to do QSR, structure-based drug designing. Now it is the era of agentic AI. So very simply, what is AI? It is nothing but the making intelligent machine. AI is not a software. Okay, it is nothing but making intelligent machine. And under AI, there is machine learning, deep learning, and generative AI. So what is machine learning? Machine learning means we are using some algorithm, and without explicit coding, without performing explicit code, it can get the output or it can learn from the input data. So what is learn? How it learn? We will discuss it later. And what is deep learning? Deep learning is nothing but from using artificial neural network or using complex neural networks like GI and RNNs, it learned from complex data and achieve some code. And another term comes generative AI. That is, we are using ChatGPT, that is generative pre-trained transformer. So 2 words, generative and pre-trained and transformer. 2 words, generative and transformer. So transformer is a very big field. So we can to prepare our virtual assistants, we can achieve our goal where human cannot do some more, AI may work there. So the actual AI actually starts in the year of 1950, and in 2025 is the era of AI. People are running behind it. So we can classify the era AI in various ways based on their capabilities and functionalities. I'm not going to discuss it, and I'm also not going to discuss this. So practically, machine learning is sufficient to solve most of the problems associated with science, and deep learning is required for complex like drug or for finding synthetic routes, that is retrosynthetic analysis. Because if you want to perform retrosynthesis, you need strong knowledge of organic chemistry. But using known data, if you train a model very easily, you can develop your own model. It will perform retrosynthesis analysis, and if you feed the data, what are the chemicals and facilities you have, it does the literature for you, and it will protocol, then how you can achieve your goal to synthesize this molecule in your lab using this condition chemicals. So what to discuss what is it is in future. Now, so we know, I'll take some time here and I'll finish. You see it is our normal neuron. It is our neuron. It's this is dendrite, and this is axon. In case of artificial intelligence, these dendrites are nothing input layers. These input layers are connected with the cell body with weights. And the cell body contains two things. One is weight term, or it is also called biases, and some activation function. So it is your skill. Why using AI is not your skill, but using this activation function to goal to get good result is a skill. So how AI works here? If we feel today is cold, so my brain neuron give me a signal, go put up the AC. And if it is hot, it will give me a signal, put on the AC. But in case of artificial neural network, how it works? Suppose we have a data table, we have variable 1, x3, and we have an dependent variable y. So you remember this factor terms 0.5, 0.7, then we can pass it through a neural network. Inputs input is not equal. Initially, we will not. So prediction 0.7. So the difference is called loss. Now it will perform some back propagation and some calculations to update this and bias to get a result very near to this prediction. This is the very basic and brief explanation of AI. So in the forward propagation, we adjust the biases and weights. Ultimately, we will get our result, which is very near to the actual result. Now, how it learned? It learned by adjusting the weights and biases. So this is the bias. How it works? It has some mathematics. I'm not going to discuss. So, what is this weight? Suppose we are going to purchase a home, and this house is before purchasing some house, we have to check how far the house is or the flat is from the city, how much square foot it is, what is the how many bedrooms are there, how old it is. So these perspectives are different for everyone. So according our for me, I need a house very near the city. So priority 1. Okay, and then I need very 2 or 3 bedrooms, so it should be 2. In this way, I'll give the weightage as an importance, and in this way, I'll set up the artificial intelligence, artificial neural network. And for a drug design perspective, the molecular weight sometimes matter more in front of in compared to log p. So I give more weight to molecular weight in rather than log p to build the network. And this is the bias, how the bias works. I'm going to explain maths behind it. So very simply, I'm going to tell you one important key aspects. That is generally we use ReLU, that is rectified linear unit function to design a model. It gives if your input value is 0, then it will return 0. If it is greater than 0, then it will be high. Else, when you train the model, it will forget what is the property of previous molecule. So I know in the way I am telling, people may not connect it with the basic because the time constraint. It is very difficult to explain everything. So these are the 3 scientists generally who discover backpropagation, and for today's neural network is possible. So neural network that we are using is single network is called perceptron, but we are using MLPs, multi-layer neural networks, and generally we use RNN, recurrent neural network, and LSTM, long short-term memory neural network. Now the thing is, brains, so network, this is a network. So there will be some feature. When it pass to another network, the loss function will be very, very high. So to optimize it, it will optimize the weightage and process and try to minimize it, and which for vanishing function, vanishing gradient. And that's why previously your LSTM model, which can remember the features of previous molecule and what are the important features are there in the we are having the new and we combining them and we can design new molecules. So it is another technique that is called convolutional neural network, and from a large sensor we extract important features and feed it to a new model. And software various large amount of important features, and we from this specifically use we design new molecules using another rough neural network and things generally used sequence of your length information are not available. This graph neural network by analyze the extract and model equivalent neural network also consider the angle. So these are the literatures. One can go over there and check it. And I'm not going to discuss transformer how when we use Google transformer, if we say it's so cool, it's not it in some different language, it will convert it in native language or my desired languages. Or if we prompt something in ChatGPT or Gemini, how it gives me response. So behind this, the thing is the technology transformer. So Google published the concept of transformer in a conference in the year 2017, which transformed the future of AI. So hope in someday so I'm not going to discuss how we get it, what is the code, Python code generally we use for designing AI. Next, we jump address a question: does AI, artificial neural network, is the AI? The answer is no, because AI may be rule based or maybe data driven. So if it is rule based, there is no use of artificial neural network or DNNs. If it is data driven, then NN. And what is machine learning? It is nothing but the subset of artificial intelligence where machine can learn from the input data without explicitly programmed. So machine, there are two types of data generally we use. There is labeled data or unlabeled data. I'm not going into what is labeled data. So another type of data we use in pharmacy, there is sequential data, there is a DNA or a protein sequence, there is a graph data, there is your molecular structure. Then in biology, we use a time series image and multimodal data like your ECG data, UHG data, or your molecular dynamics, movies and all. So using this data, we can perform machine learning in supervised, unsupervised, and reinforcement learning. But in pharmacy or in drug discovery or in chemistry related things, we use only supervised and unsupervised learning. So I'm not going to discuss what is machine learning, what is supervised and unsupervised learning, and what is the algorithms. Actually, it is important what algorithm we want to implement in our machine learning model. So generally, we use random forest for classification model. It is it perform very good. Or XGBoost, it is also performing very good. I'm not going to discuss how this model work, what is actually going on in behind it, and lasso regression. This linear regression and lasso regression is good for us to predict PK, solubility, PIC50, or binding energy and all. And for unsupervised learning, we use k-means clustering or PCA analysis. So these are various parameters. So we can use it to evaluate how performing, how my model is good or not, how it's performing, what's the sensitivity. And here is our work. I'm showing we develop one ML pipeline for everyone. It is called Easy ML. So the thing, hello.
Sir, please,
Yeah,
conclude.
yeah, in 5 minutes, sir. So we discuss it in future. So this is our ML ECM that we develop. It automatically takes the data from the website. It automatically build the model, give the statistics, give you all the result, what will be the predicted activity, and what is the performance of the model. And also we develop some tool like Anushandhan. It is for virtual screening in Windows system. Yet not other than Pyrex, no software is available. And for chemical conversion and smile to various structure conversion, we have some tools. We develop a tool called Anuprabha. That is a molecular dynamics simulation tool. We use Amber in the background, and this is our Easy ML. So fully automated tool. These are some publications, and in depth we will discuss some. Thank you.
Thank you, sir, for your nice presentation. Now platform is open for the discussion. If anyone have any query on his presentation, so you may ask one or two questions.
Sir, due to lack of time, I want to say if anybody has any question, my name, if they type in Google, they can find my email ID, they can directly email me. We'll discuss, you can proceed for your further.
Okay. So we are letting the time. So if you have any query, then directly you may send your query, or you may discuss with Dr. Devanjan Sen sir through the mail, or he will share his email ID and contact number. So later on we can continue our discussion. So sir, thank you for your nice presentation on the machine learning.
Thank
It is
you,
very
sir.
emergent
Thank you,
topic.
and Vomik, ma'am.
Yeah. Yes.
Thank you,
So,
sir. Thank you,
yes.
sir. For a long time, after a long time, we see each other. And Bhumik, madam, you total your fraternity. Thank you to you all for the privilege. Because the lack of time, I just briefly run over it because it's a very
exactly.
time-consuming things. Okay. Bye, bye, sir. Thank you.
Okay. Then our next OP presenter is Dr. Orup Patari. Dr. Orup Patari is present here.
Yes, I am present.
Sir, continue your presentation. Your time is 8 to 10 minutes. Sir. Thank you.
Okay. Good afternoon to everyone. The title of my paper is Enhanced Activity of Solar Cycle 25 and its Impact on Ionospheric Total Electron Content Variability, a study on two early strong and severe geomagnetic storms occurred during 23 and 24th March and that of April 2023. This is the outline of my presentation. Uh, this is about the ionosphere. I am not going through details. And here the importance of ionospheric study or ionospheric research, because we know it is the age of internet, satellite communication and all this. And in this field, ionosphere plays a very important role because this ionosphere can modify the radio wave which is used in these fields. Uh, this is our GPS system, global positioning system, basics of global positioning system, three segments, space segments, user segment and control segment. This is our instrument which is installed at Tripura University CIC. It is GPS track monitor. It has different parts, data acquisition system, antenna, and a computer system. And this works on the principle of GPS. GPS technology is actually introduced here. We know the radio waves used in this GPS technology is modified by the ionosphere. So if any disturbance occurs in ionosphere, so a signature is left in the radio wave. That is, radio wave carries the signature of disturbances in the ionosphere because it passes through the ionosphere. So on this principle, the GPS track monitor works. Here we are interested an important parameter of the ionosphere, total electron content. It is nothing but the total number of electron in a column in a cylinder having unit cross-sectional area and distance from the length equal to the satellite and the GPS device, the total number of electron in such a cylinder. So this is about geomagnetic storm about which we are interested. It is nothing but the enhanced injection of solar energy into the Earth ionosphere, magnetosphere and thermosphere system. It mainly occurs due to the solar disturbance, coronal mass ejection, CIR, and all these events which occur in the sun. This is the solar cycle. We know solar cycle is nothing but the description of variation of the magnetic field of the sun in a period of 11 years. We know the inside atmosphere of the sun is not steady, it varies, its magnetic activity varies. So in each 11 years this magnetic activity is repeated. Now we are going through the solar cycle 25. Now what is the speciality of this solar cycle 25 is that the red line shows the predicted cycle path, but the actual dotted graph shows the actual activity pattern. So it is clear that 25 cycle has the enhanced activity. The activity is higher than the predicted value or pattern. This is the data sources from the. We have considered two geomagnetic storm, as I have mentioned. One first geomagnetic storm has the DST values minus 155, and the second one has DST values 213. So second one is a little bit severe than the first one. So these are the experimental result. The left uppermost graph shows the variation of different parameters, solar, interplanetary, and geomagnetic indices. Here, red arrow is the downward arrow shows the initiation of the geomagnetic storm, and the lower graph in the left panel shows the variation of the total electron content, that is ionospheric density. We have considered 6 days, 2 days before the geomagnetic storm and 2 days after the geomagnetic storm, including the days of geomagnetic storm. Actual geomagnetic storm occurs at the 24th March. So here we see a very significant fall of the total electron content in the recovery phase. That is 1, 2, 3, 4 at the 5th day. There is a huge fall in the total electron content values in the recovery phase, and the right panel shows the variation of the O by N2, that is the thermospheric composition variation of the oxygen atom and other charged particles. So this variation in actually our station of interest is Agartala station. So near Tripura, the variation of O by N2 supports the variation of the total electron content. This is our second event. Here we see at the main phase there is a fall of total electron content. That is on the 24th of April. So the fall is near about 10 tech unit. In the previous case, it was 60 tech unit. So here in the second case, though the geomagnetic storm is severe, more active than the previous one, here effect is a little bit less in compared to the previous one. The the right panel shows the variation of the O by N2, which supports which explains the variation of total electron content. So here is a detailed results. As I have told.
Sir, please conclude, sir, 1 or 2 minutes, sir.
Okay. So what is the remarkable result? First storm was strong and the second one was severe. But in result, we see that in first case, the variation in tech is much more than the second one. So the discussion, the results can be explained from various with various mechanisms like the penetration of prompt penetration electric field, variation of O by N2 as I have told, and disturbed dynamo effect. Through all these mechanisms, this result can be explained. So here one thing is to be mentioned, that the understanding of enhanced activity of the present solar cycle 25 needs more theoretical as well as experimental investigation, and in conclusion we can say that this investigation contributes much more in the realization or understanding the mechanism of the ionosphere and solar atmosphere coupling, and overall analysis of these two early strong geomagnetic storm of solar cycle 24 contributes a deeper understanding of ionospheric variability, provides valuable insight into the mechanisms governing storm time electrodynamics in the near Earth. So, and such type of investigation may help in forecasting of the solar atmosphere or solar weather in near future. So thanks. These are the references. Thanks to all.
Thank you, sir, for your nice presentation. Due to the shortage of time, we are just moving the next presenter. If anybody has any queries, so you can communicate directly with Dr. Arup Patel, sir. Thank you, sir. Our next presenter is Gurvinder Singh. Are you present here?
Yes, sir. Am I audible?
Yeah. So please confine this time to 10 minutes, please, because we are running behind the time.
Sure, sir.
Yes, you can start.
So, good evening, everyone. Uh, as the shortage of time is there, so a brief introduction to the topic is ultrasonic and thermodynamic investigation of sodium chloride and sodium sulfate in the aqueous solution of sodium salicylate. So, my work is under Dr. Nabakarna Chakrabarti, and I am a student of Lovely Professional University, currently pursuing my graduation, and this is my part of capstone project. So, moving to the definition, ultrasonics is a branch of physics or sound waves which deals with the frequency above 20 kilohertz. So these are
ভিডিও
the
অ্যাডজাস্ট
sound
হবে
waves,
নাহলে কত আনবো কত লাগবে অনেকবার
sound waves which are above the human audible range. So it is a non-destructive technique. For example, if you place a sample in the ultrasonic technique, it will not affect the internal structure. So if a structure has a pattern of ABAB, so it will not deviate the internal structure. So this is why the it has a wide use in medicine, safety, research, and industries. So these thermoacoustic techniques provide the inter and intermolecular interaction of liquids at various molalities, at various concentration, at various range of temperatures. So with this help of techniques and parameters, we could easily determine the deviation from the ideal behavior. So with deviation, we could easily get an insight what kind of interactions are happening. So the materials on which the investigation was done, the it were sodium chloride and sodium sulfate with the sodium chloride and distilled water. So sodium salicylate is widely used in medicine, skincare, cosmetic, and food industry as a preservative. So due to the anti-inflammatory drug, it is widely used in medicine. So it is an alternate to aspirin as well, helps in reduction of the pain, helps in the reduction of the fever. And sodium chloride, as you all know or are aware of, that is common salt. So it is an ionic compound and is a strong electrolyte. So the helps in metabolic activities of the living organism. So these two solutes, that are sodium chloride and sodium sulfate, that helps in the activities of living organism. So the methodology was a sample of distilled water with sodium salicylate and chloride and sulfate were prepared at different concentration of sodium salicylate and different molalities of sodium chloride. So the sample was prepared, and after this, it was injected to the DSA, that is density and sound analyzer. So after the injection of the sample in the DSA, values of the density and speed were shown on the screen. So with these two values, we could have six parameters. So what are the those six parameters that are in the further slides? So first parameter is the impedance. So impedance, as you all are aware of, is a form of resistance. So in physics, there is a resistance, resistivity, and also impedance. So impedance is a product of density and sound speed. So in the previous slide, as you are aware of, DSA provides the density and speed. So when you multiply both the parameters, you will get acoustic impedance. So increase in impedance is seen with increase in molality. As you can see on the x-axis it's molality and on the y-axis it's acoustic impedance. So with the increase in molality, there is an increase in impedance. This states that because the molality increases, the ions that are like sodium chloride ions, that will make more amount of ions are liberated in the specific what do you call sample. So more amount of the concentration, more amount of the interactions are happening with increase in molality. So more number more the amount of the ions liberate, more is the association, and more is the impedance to the sound wave. So these next parameter is adiabatic compressibility. So this is a kind of relation between the density and again sound speed, but it follows the inverse. So more is the ion, more is the association, and lesser is the compressibility. So if you imagine like this, Na positive will when combined form a structured or a what do you call a less compressible state. So this can be further verified from the figures itself. As you see in the two-way figure, with increase in molality, there is a decrease in the compression. So with the association, the state is less compressible. Moving on the third parameter, that is Wada's constant. It helps in the molecular packing and interaction that are expressed in the terms of compressibility and density. So increase in impedance slightly increases the Wada's constant, but it shows opposite behavior in the molality and molality. So increase in molality, it shows a decrease in Wada's constant. This further states that there is a strong solute solvent interaction within the aqueous solution. So the 3A, 3B, 3C parameters are for sodium chloride, 3D, 3E, and 3F parameters are for sodium sulfate. So with increase in molality, there is a decrease in Wada's constant. Further, we have Rao's constant, or another name is molar acoustic velocity. So it's the effective volume occupied by 1 mole. So see, as the associations are taking place, there is a reduction in the volume, right? So if the molecules are freely before the application of the sound velocity, and when the molality increases, there is a association and there is a reduction in the volume. So this could also be varied from the figures itself. So see, in increase in molality, decrease in Rao's constant. Furthermore, we have van der Waals constant. It's the
Yes, sir.
uh, ac-
Sir, please conclude
pardon,
in 1 or 2 minutes.
sure. So what is constant is the excluded volume or the co-volume of the molecules. So it also shows the same relation because it's excluded volume. So there is a reduction in the excluded volume when the association are taking place, which could also be verified from these figures itself. Now we have the intermolecular free length. So this is the average distance between two molecules. So if the concentration is increasing, associations are taking place, there is a decrease in the volume. So the molecules are tend to come closer to each other. So there is a reduction in the intermolecular spacing or free length. But on the other hand, there is a slight increase in intermolecular free length due to increase in temperature, because the increase in temperature causes increase in kinetic energy of the molecules. So when there is a kinetic energy, there is a expansion. So when there is expansion, there is the molecules tend to separate or tend to move far from each other. There is a slight increase in the intermolecular spacing. So if you see from these tables, uh, from on the extreme left, there is a decrease in intermolecular free length. So in the conclusion, we concluded that there is an increase in ion solvent or solute solvent reaction when there is an increase in concentration of chloride or sulfate. So, but addition of solute makes it more ordered state. This could be concluded. But the increase in temperature increases slightly parameters like intermolecular free length, van der Waals constant, Rao's constant, and Wada's constant. This indicates there is a disruption or structural breakdown or expansion of the volume. And in comparison to both the solutes, that are sodium chloride and sodium sulfate shows higher values because sodium sulfate is a liberates two ions rather than one chloride ion. So what is the future scope of this? So molecular simulation can provide deeper understanding. So these interactions, when studied under advanced studies, So we could better conclude what kind of interactions are taking place, and this could help in drug design and drug formulation. So what these are the references which I have added on. So thank you everyone for listening to my presentation.
Thank you, Guruvinder Singh ji,
Thank you, sir.
for your nice presentation. And our next presenter is Kaur Navadip. Are you present here?
Yes, sir, I'm present here.
Yeah. So please confine
Okay.
time 8 to 10 minutes. You can
Okay,
start your
sir.
presentation. Okay. Thank you.
Okay, sir. Let me share my slide. My screen is visible, sir?
Yes, yes, it is visible.
Okay. So I'm going to start. So good evening, everyone. So I am Navdeep Kaur from Lovely Professional University, and I'm a research scholar under the. And today I'm going to present molecular insights into acousticals and thermodynamics property of the sodium dodecyl sulfate with mono and trisodium citrate. And this work has been carried out under the supervision of Dr. Navapanna. I will briefly present the introduction, experimental design, results and discussions, comparison between mono and trisodium citrate, and then followed by the applications, future scope, and the conclusions. So ultrasonic techniques are the non-destructive and sensitive method which is used to study the molecular interactions in the liquid system. While sodium dose, in this work I have used sodium dodecyl sulfate with the citrates. It is an ionic surfactant. It is studied in the presence of mono and trisodium citrate. So the objective of this study is to understand measles formations and intermolecular interaction using acoustics and thermodynamics analysis. By finding out the various parameters, these interactions plays an important role in in applications in pharmaceuticals and further industrial use. So here, this is my industrial design. This system consists of SDS with mono and trisodium citrates and over a molality range of 0.0 to 0.5 moles per kg and temperature range of 288 Kelvin to 318 Kelvin, that is basically in 15 degrees Celsius to 45 degrees Celsius. Density and velocities were calculated, measured using this instrument, Enterpan DSA 5000 M. From these calculated parameters, from these observed parameter densities and ultrasonic velocities, these measurements were done that from these measurement parameter like acoustical impedance, adiabatic compressibility, intermolecular free length, Laws constant, Vada constant, and van der Waals constant. So these are the standard equations used to calculate the acoustic and thermodynamic parameters. Now I will discuss the result. So in general, now coming to the result, here this is a graph of, this graph shows the variation of ultrasonic velocity with molality for SDS in the presence of monosodium citrate at different temperature. It is observed that ultrasonic velocity increases with increase in molality, and at all temperature also the velocity increases from the temperature range, as we can see here. So this indicates stronger intermolecular interaction, and closer molecular packing due to mesal formation in the system. This suggests enhanced solute-solvent interaction and structured online. In my next slide, here we have a similar trend is observed in case of trisodium citrate, but the in case of, however, the values of ultrasonic velocities are higher as compared to monosodium citrate. This is due to higher ionic strength, because in monosodium citrate we have a one sodium atom. Here we have three sodium atoms. Now moving to the next parameter. Next is here when we see this is what we measure from that enter path. This is the density. So density increases with concentration, which suggests enhanced solute solvent interaction and structure ordering in the system. Same kind of trend is also seen with the trisodium citrate. Further is so this is a calculated parameter, drive parameter, using the values of density and ultrasonic speed. So here adiabatic compressibility, when we see that, they also increases with molality, which indicate that there is an increase in resistance for both the system in case of monosodium and in trisodium citrate also, but which indicates increased resistance to the sound propagation due to tighter molecular packing. So next is our adiabatic compressibility. So adiabatic compressibility is basic how much we can ease of compressing any of our system. So adiabatic compressibility, here we can see it decreases with concentration, indicating reduced free space and increased rigidity of the system. Generally with temperature it increases, but here the compressibility of any system increases with temperature, but here in our system it decreases. Why? Because of the strong interaction of due to the mesals and citrate ions, and these ion surfactant interactions at high temperatures shows that there is a mesal formation which become more favorable for the hydrophobic interaction, and it increases. So the result shows that there is a more compact structure, and this is more prominent in trisodium citrate as compared to monosodium citrate. Now the next parameter is Wada's constant. Here the molecular Wada's constant is a molecular association that it tells us what is structure compactness and the molecular association, how tightly the molecules are packed in the system. Here the values of this Wada constant decreases with molality for both the system in monosodium and trisodium citrate, while with temperature there is slight increase with temperature. So this is due to molecular arrangement and interaction dynamic, which suggested there is a progressive structuring of the system with increase in ions as compared to mono and trisodium citrate. Now next one, my parameter is Rao's constant. Here it decreases with molality and increases with temperature. And change why it decreases? Because there is change in molecular association and structure arrangement in the system, and with increase in temperature there is a molecular motion which enhanced in dynamic interactions. Okay, so the combined Rao's and Wada constant together, they show that the system variation indicating change in molecular association and structure compactness of the system. So here in intermolecular free length, it
Please,
decreases with increase in
please
molality.
conclude within 1 or 2 minutes, please.
Okay, sir, I'm about to just conclude. So here's in van der Waal, the variation in van der Waal constant suggests changes in effective molecular volume and solute solvent interaction. From the experiment data, it is observed that ultrasonic velocities, density, acoustic impedance, they increase, while the other parameters they decrease with molality. Here, the trend is also observed with the temperature. On the other hand, density decrease with temperature, velocity, caustic impedance, and Rao's constant, Vada constant, and they all increase with temperature. From the observation, we can interpret that like for like ultrasonic density is for compactness. Now it increases, shows that there is a closer packing and structure solvent, strong solute solvent. And in ultrasonic velocity tells us that there's stronger interaction strength, so it increase indicate that stronger intermolecular interactions are there and better structure organization. Acoustic impedance, this is a resistance to sound propagation, so it reflects that the system is more rigid and structured. So adiabatic compressibility, it is the ease of compression, so decrease indicate reduced compressibility and stronger interactions. So Wada constant, it tells us about the structure compactness, while Rao's constant tells us about the molecular association. Their decrease suggests that there is a structural rearrangement, and which indicates that there is a more compact structure. While intermolecular free length, it decreases. So this is a distance between molecule. It decreases, indicates that shows that molecules come closer, increase with temperature due to expansion. So van der Waals constant is effective molecular volume or the free volume. So decrease show that reduced free volume. There is a tight packing and increase with temperature due to expansion. So here there is a comparison. When we see the comparison, in case of trisodium citrate, they forms a because of the presence of more iron, they form a more compact structure. Here this is not much ordered, but there's an ordered structure, strong intermolecular force, which leads to the enhanced meso formation and structure compactness. So these are the practical applications, as we can see. So in case of practical application, we are using, these are some of the practical applications, like these findings are useful in food industries, pharmaceuticals, green chemistry, for the further surfactant based industrial applications, and for the drug delivery system. And the future scope, future studies can include like FTIR analysis and theoretical modeling to gain deeper insight into the molecular interactions and finding the other components, advanced thermodynamic parameters. So this is a conclusion. In order to conclude that increasing electrolyte concentration enhance intermolecular interaction and promotes meso formation. And this study shows significant change in acoustical and thermodynamic properties with concentration and temperature. While trisodium citrate, it exhibits stronger effect as compared to monosodium citrate. These are my list of references, some of the references, and I would like to acknowledge sincere thanks to Department of Chemistry, GNDU, for providing me lab facilities, and I'm grateful to my supervisor, Dr. Nabapanna and Dr. K.C. Juglan. Thank you for your attention. Thank you so much, sir.
Thank you,
Yes.
Navadip Ghosh, for your presentation. Our next presenter is Devasri Chakraborty. Devasri Chakraborty, are present here? Devasri Chakraborty,
Yes,
are
sir.
you present here?
Yes,
Okay.
sir. Yes, sir.
Okay, then you can start your presentation.
Okay, sir. Am I audible, sir?
Yes, yes.
And
Slide is
my
visible. Yeah.
is visible. Just a minute. Good evening, everyone. Myself, Devasri Chakraborty, the Department of Chemistry, NIT, Agartala. Today, I will presenting our research on exploring nitrogen-oxygen coordinated isophenolated versus carboxylate binding in dimethyl tin complexes, a DFT study. This work focuses on understanding how different ligand binding modes influence the structural stability using both experimental and theoretical approaches. Now, the background of our research. The organotin compounds are significant in material science and medicinal chemistry. The ligand here is used 4,2,4-dihydroxyphenyl azobenzoic acid, which is multidendritic. It contains two competing binding site. One is carboxylate group, another is azophenolate groups. Now our objective is to determine which binding site dominates coordination with tin center. Most literature focuses on carboxylate tin coordination. However, nitrogen-oxygen chelation via azonitrogen and phenolic oxygen is rarely explored. The question is nitrogen and oxygen chelate thermodynamically more stable than the carboxylate bond? Because the real chemical system exists in solvent environment, not in vacuum. We propose three isomers where one tin is bonded to carboxylate group, and in 1B it is a 6-member nitrogen oxygen chelate, and 1C a 5-member nitrogen oxygen chelate. All structures show distorted tetrahedral geometry around the tin center. The central goal is to determine which isomer is the most stable and experimentally relevant. We used a combined experimental and theoretical approach. In
Devasri,
experimental, yes sir,
your slide is not moving.
sir,
Just
not moving it.
no.
Okay, sir, just a minute.
Yeah, now it is moving.
Okay.
Yeah, now it is moving. You present your crucial finding only. Okay.
Okay, sir.
Yeah.
Now, we used combined experimental and theoretical approaches. In experimental, the synthesis using dimethyl tin dichloride, tin NMR used for geometry identification, 13C NMR used in coordination confirmation, FTIR for functional group analysis. In computational, the DFT for geometry optimization, gas phase versus solution phase comparison, and TDDFT for UV visible spectra analysis. This integrated approach ensures high reliability of conclusion. Now we move on the geometry and structural feature. All isomers exhibit distorted tetrahedral geometry. However, the key differences arise in bond angles. 1A shows 60 degree, 1B shows 80 degree, and 1C is 71 degree. We know that the lower angular strain, the greater stability. Thus, the 1C show the most favorable geometry. Now we move on the thermodynamic stability. Now the most important DFT result in gas phase, we see that one isomer 1A is slightly stable, but when we added solvent into it, we show that 1C isomer become the most stable one. The 1C is favored over 1A by a massive energy shift around 1269.45 kilocalorie per mole. This is a dramatic shift. Now we can say that the solvent stabilize nitrogen oxygen chelate more effectively. This highlights the importance of the including solvent effect in DFT studies. Now we move on the spectroscopic evidence. From FTIR, here the experimental IR spectra show that the highest correlation with the calculated values for isomer 1C. Particularly, the carboxylate OH stretches at 3239 centimeter inverse. In 13C NMR, we can clearly see that here carboxylate carbon show a minimum shift, which is ruling out the possibility of carboxylate coordination. And when we see in teen NMR, there is a single peak around at 114.95 ppm, which is a characteristics of 4-coordinated distorted tetrahedral geometry. Now we're moving on homolumo and UV visible spectroscopy. From homolumo analysis, we can clearly see. Yes, sir.
Please conclude your within 1 or 2 minutes.
Oh, sir. Okay, sir. It is. Here we see that 1A show the 3.25 electron volt, 1B show 1.92 and 1C show 1.3 electron volt. We know that lower the energy gap, the higher reactivity. Thus, 1C show balance, stability and reactivity. And we see from the UV visible spectra that our experimental spectra arise in lambda max 390, which is when we see in 1C isomer, is it around 362.55. This is, so we can say that 1C is a correct structural model. Therefore, the various structural analysis, including bonding, geometry, and calculated angle, we can prove that 1C complex is favorable one and experimentally relevant. In conclusion, our work show that we cannot depend only on the gas phase model alone, but by the combining the spectroscopy and the solution phase DFT, we can prove that 1C isomer is more dominant one and structurally favored. This study proved that if we go through the both experimental and theoretical, there we can design in future in these types of complex more accurately and precisely. Thank you.
Okay. Thank you, Devasti, for your presentation. Our next speaker is presenter is Nayan Mandal. Nayan Mandal, are you there?
Yes, sir.
Yes. So you start your presentation. Your time is 8 to 10 minutes.
Okay, sir. Good evening, everyone. I am Noyan Mandal from BCTA College of Pharmacy and Technology, Department of Pharmaceutical Chemistry. My presentation topic is proteomics-based network analysis for dark target exploration. In this presentation, I share a brief overview of how proteomics analysis work in disease target prediction. At first introduction, what is proteomics? Proteomics means all about protein. Proteomics is the large-scale study of the proteins in a biological system. It studies protein expression, structure, functions, and interaction. Basically, traditional drug discovery focus on one target at a time, but proteomics gives us a system-level view. Means we study the whole network, not just a one protein. Next, network biology concept. Basically, biological system work like a complex network. Network biology help us understand how protein interact with each other and how disease work. There are mainly three types of biological networks. One is protein-protein interaction network. Next is gene regulatory network. Another is signaling pathway. Then the workflow of the drug target exploration pipeline. Basically, system work like it is several. Basically, drug target exploration follows several stages. First, we take input data, which is query protein. Then go for target mapping. Then we go for the build a network. After that, we go for the topology analysis, perform pathway inference analysis, refine result, and finally classify the drug targets. Here is the various data source and tool we can use. Some useful tools are Pride and Proteome Exchange. These are global database that store proteomics data. Sting, it is a database used to visualize the protein-protein interaction network. Cytoscape used to analyze and visualize the biological network. And Stitch, which map the interaction between chemical compound and a protein. Next, protein-protein interaction network. In a protein-protein interaction network, each protein is sourced as a node, and the connection between them are called edge, and the thickness of edge describe the connection strength. By analyzing the network, we can identify half protein, which are the highly connected proteins and key regulators that control the disease pathway. Here is a diagram how to work the cytoscape to build a network. Next, the key network matrix. Several metrics are there for analyze network. Some of them are the decrease centrality, betweenness centrality, closeness centrality, and clustering coefficient. Then network analysis and functional inference. Network analysis help the identify the half proteins, clusters, and pathways. Functional inference is used to predict the functional and unknown proteins. Group of the functionally similar proteins. This gives us a complete system level picture of disease. Here is the functional arrangement image of the some proteins. Then the drug target identification. In the process, we identify a protein. Those have the potency become drug target. Various factors are there for target identification, like those protein involved in disease pathway. Using network analysis, we identify the key regulatory protein that are the disease associated and can bind to the drug. Half proteins with high connectivity are the best drug target. Next, the application and limitation. This approach helps identify novel drug target, understand the disease at the system level, predict off-target activity, support personalized medicine, and even repurpose of the existing drug. And the limitation, however, the data set are the large and complex. There can be false positive interaction. Protein behavior is not always fully known. Advanced tools are need to and combining data from multiple sources in the challenging. Then the conclusion, to conclude, protein-based network analysis give us a powerful system-level view of disease by studying protein interaction. It helps to identify key drugs and pathways. It improves the target therapy development and support personalized medicine. Despite challenges, it is a very promising approach in the modern drug discovery. Next, there are the key reference used for this presentation. That's the end of my presentation. Thank you for.
Thank you. Thank you, Noyan Mandal, for your presentation. Our next paper presenter is Nilendu Pal. Nilendu
Yes,
Pal
sir.
is there?
Yes,
Okay.
sir. Yes, sir.
So, sorry, please start your presentation. And your time is 8 to 10 minutes. Thank you.
Good evening, everyone. My name is Nilendu Pal. I am a Master of Pharmacy student in Pharmaceutical Chemistry at BCDSCPT Hidayapur. And today I will talk about AMBER, a complete package for molecular dynamic simulation. And here is the introduction part. What is AMBER? And at first, what is AMBER? AMBER is a very important tool used in the field of molecular dynamics, and it helps scientists simulate and study how biological molecules interact each other and likes proteins, DNA, and move and interact with each other. And then what the term AMBER refers to the two things. At first, it is a set of molecular mechanical force field, and then it is a package of molecular simulation program which includes source code and demos. Then the importance of MD simulations in drug discovery. At first হচ্ছে যে the biological molecules like proteins and drugs are not stiff or fixed, and they are always moving. And they are always bending and changing the shape, and this movement is very important for how they work in the body. And techniques like X-ray crystallography, NMR provide static snapshots, and MD reveals the time-dependent interaction. Why MD in the pharma? It predicts mainly the protein ligand binding modes. Docking alone is insufficient, and study conformational changes like allosteric regulation, enzyme mechanism, and estimate the binding free energy like MMPBS and MMGBSA. And why AMBER? AMBER is best, and it is a gold standard software for biomolecular MD and integrated workflow, that is the preparation, simulation, analysis in one software. And it is mainly optimized for the GPU acceleration, because it have the PMEMD.CUDA engine. Then the basic workflow of AMBER. And now let me explain how AMBER actually works step by step. And I will divide it into three simple phases. At first, the prepare, and the simulate, and then analyze. At first, the prepare the system. We start by taking the protein and protein data complex from the PDB, protein data bank, and then add the hydrogen atoms and counter ions like sodium, calcium, chloride ions, and then we use solvent box using TIP 3P water, and assign the appropriate force field for protein FF14SB, and for ligand anti-chamber. Then two output file is generated, and one is topology file, one is coordinate file. And then then the energy minimization procedure, where we remove the bad contacts and relax the structure before the dynamics. At stage 1 we minimize the solvent only, and stage 2 minimize the entire system. Then the system is heated from 0 Kelvin to 300 Kelvin using NVT ensemble, where the volume is constant and the temperature constant always, and weak resistance on the solute to avoid the structural collapse. And then the equilibration procedure, where system is stabilized at constant pressure and temperature, and where typically duration 100 to 500 picoseconds. Then the production of MD. The production of MD, for the production of MD mainly seeks mainly PMMD.CUDA or main MD or
Hello, hello, hello. Nilendu, are you ready? আছে কিন্তু একটু প্রধানটি you may conclude your presentation. Okay. Thank you, Nilandu, for your presentation. I think there is a network issue with you. So we can go for next presentation. Our next presenter is Polobi Shina.
Yes,
Polobi
sir.
Shina, are you there? Okay.
Yes, sir. Am I
So
audible?
yes, you are audible.
Okay.
So you could start your presentation. Please conclude your presentation within 8 to 10 minutes.
Okay, sir.
Thank you.
Sir, my screen is visible?
Yes, it is
Okay.
visible.
Okay, sir.
Clear.
Good evening, everyone. My name is Pallavi Sinha from BCT College of Pharmacy and Technology, Department of Pharmaceutical Chemistry. Today, I will be presenting my seminar on the topic is harnessing natural products for drug design via scaffold hopping. Here is a quick overview of what will I cover today. Then what is natural products? Natural products are bioactive substances found in nature from plants, microbes, and marine life. They are very important in drug design. In fact, nearly 50% all of FDA approved drugs come from natural products. The main famous examples are morphine, artemisinin, paclitaxel, camptothecin, etc. Then scaffold hopping. Scaffold hopping is a technique where we replace the core structure of drug molecule with new one, but the biological activity remains same. We use this to improve how a drug is absorbed, reduce its side effect, and make it more effective. There is a three type of scaffold hopping: classical hopping, topological hopping, and natural product inspired. Then, why is the scaffold hopping important? It helps us create more diverse drug molecule, avoid toxicity, improve bioavailability, overcome drug resistance, and even get patterns for a new drug design in pharmaceuticals industry. Then the strategies and workflow. At first, for our study, we used several computational tools, ChemDraw for drawing molecules, Autodoc Vina for docking, which tell us how strongly a drug molecule binds to its target, Swiss ADME and PKCSM for checking the drug safety and drug likeness, and IMODS for checking the molecular stability. Then the workflow pipeline. Our workflow had 5 steps. First, we selected target proteins like ACE2 from the protein data bank. Then we selected our natural compounds as a ligand. We performed molecular docking for find the binding energy. Then ADMET screening for drug likeness. And finally, we perform the stability analysis using NMA. uh, Here, natural products inspired scaffold design. Based on our network, some researchers designed new scaffold inspired by natural products, modifying their core structure to improve drug properties while keeping their biological activity. Then the next slide, marine sponge metabolites. We also looked at compounds from marine sponge, which are a rich source of anti-cancer activity. These were screened through our pipeline to find the potential anti-cancer drug candidates. Here the case study. Our first case study is quinimbine, which is isolated from curry leaves. It shows the strongly binding to the SARS-CoV-2 target, especially binding with the MPRO gene, and it also showed an anti-cancer activity, and it is very safe for normal human cell. This make it an excellent natural scaffold in drug design. Uh, then our next case study, evodimine. Our second case study is evodimine, a natural compound with anti-cancer property. Using scaffold hopping, we designed a new molecule inspired by it called indolopyrazoloquinazolinine. This is a new scaffold, has anti-tumor activity and work by stopping cancer cell from spreading in our body. Then its structure activity relationship of it. When we modify the new scaffold at different position, it found that adding orthomethyl group and fluorine group in 5 and 6 position, then we have better safety profile of drug molecule. This is what called the structure activity relationship. Some advantage and disadvantages. Scaffold hopping has many advantages like better drug diversity, selectivity, ADMET profiles. However, it also some has disadvantages like synthetic complexity, limited availability, and some natural scaffold and poor oral bioavailability. The future perspective is AI and machine learning will help us to predict better scaffold faster. Combining natural product inspired design with AI could fully automated drug discovery. Natural products like quinimine also have antiviral activity as well as anti-cancer activity. To conclude, natural products inspired scaffold hopping is a powerful strategy in drug design. Combining traditional phytochemical knowledge with modern computational tool can speed up the drug discovery. With AI and better database, this field has a very bright future. There are key references I used for this seminar, and also thank you for listening my presentation.
Thank you, Pallavi, for your presentation. Our next
Thank you.
presenter is Shomobrata Maiti. Shomobrata Maiti, are you there?
Yes, sir.
Yeah. So you can start your presentation. Please confine your time within 8 to 10 minutes. Thank you. Please start. Shomobrata, please share your slide.
Yes, sir.
Yes. Yes, it is visible. So you can proceed.
Good evening, everyone. My name is Shomobrata Maiti, Department of Pharmaceutical Chemistry from BCD College of Pharmacy and Technology. Today, I am going to present my oral presentation topic, Drug X, deep learning model and tools for exploring of drug-like chemical space. Next, I go for first slide. This is the content, and next introduction part. Drug discovery is a very time-consuming and a costly process. Traditionally, method take many years and require high investment. To overcome this, artificial intelligence is now used in drug designing. DrugX is an open source software tool that used deep learning and reinforcement learning to generate the new drug-like molecule. It can optimize multiple properties such as the activity, toxicity, and drug likeness at the same time. It is mainly used to de novo drug design, meaning designing molecule from the scratch. And go for the second slide, flow chart. Here, the past compound data. The process start with the compound data, which include the known chemical structure from the database, such as a Campbell. Next, go the standardization clean. In this step, the input molecule are standardized and clean. These include the removing duplicate and correcting the chemical structure and ensuring the consistency. Then go for the encoding. Next, the molecular encoding into the machine reliable form. This can be done using the smiley, and encoding convert chemical structure into the numerical data for AI models. Then next, the deep learning models point to right, and the encode data is the passed into the deep learning molecules such as the RNA sequence transformation and the graph transfer. Then next, the preparation and fine tune. The models are fast preparation on the large data set to learn the general chemical knowledge. Then fine tuning is done to focus on a specific target. Then the reinforcement learning. Here, after training, reinforcement learning is applied. In this step, the model generates the molecule and receive the feedback based on their quality. Then source, each generated molecule is evaluated using the scoring function. The score is based on the properties like activity, toxicity, or drug likeness. Then generate, based on the reinforcement learning and scoring, the model generates a new optimization molecule. Then the focused virtual library. Finally, this generated molecule from a focused virtual library, which can be used for the future drug development and testing. Then the next slide, material and method. The fragmentation. These figures show the complete workflow of DrugX. Fragmentation in this first step, the input molecules is broken into the small fragment using the fragmentation method like bricks. And second, encoding. After the fragmentation, the molecules are converted into the machine reliable fragment, which is called the encoding. Encoding divided in three parts. One, smile encoding. Two, second one, smile fragment pair encoding capture, and third one, grab encoding. And the next step, the generator. In this step, encode data is passed into the deep learning models called the generators. This is the three types: sequence RNN and sequence transformer and the graph transformer. And the graph encoding details. The section explain the graph encoding is more details. The matrix contains atom type, atom index, or connected atom index, etc. The slide 4, implementation. This figure, first the figure show how DrugX evaluate molecule using the molecular weight. The user sets a lower limit 250 and the upper limit 400 to define the optimal range. While the sigma control how smooth the score decrease outside this range. Based on this setting, a scoring function is created to select the suitable drug-like molecule. The graph show the right side. The graph show how molecule weight affect the score. Molecule between 250 to 400 gets the higher score, while value below or above this range gets lower score. Molecule far from this range are rejected. This is called the smooth humping. And the lower portion, the diagram, DrugX is mainly divided into the two important parts: data and training. The data molecule handle everything related to the preparing molecule. It includes the corpus and vocabulary and dataset file. The training molecule is responsible for building and improving the model. Like it's include the generator, explorer, scorer, function, etc. Below that, there is a parallel molecule which helps speed up to computational by running tasks simultaneously. There is also a log module which stores the configuration, setting, and result, helping in tracking experiment. And the next The last conclusion, the significance of the DragX open source development, facilitating the validation and testing, user and kernel features, and addressing AI integration challenges, encouraging faster adoption or future enhancement, and some future perspective. Integrative of the novel tools for the molecular docking and retrosynthesis prediction, some key expanded input representation, enhance the user features, optimization of the models, and some key advantage, versatile architecture, open source, nutrient model, advanced molecular representation, and some limitation here, use expertise requirement, high computational demand, data quality dependency, limit customization, and thank you. And and the reference part.
Thank you. Thank you so much, Dr. Mighty, for your presentation. So our online session is almost over. Now I am requesting our organizing secretary, Dr. Subroto sir, to conclude this online session. Sir, please.
Thank you to everyone, and especially to the chairperson of this session, Dr. Pradeep Devnath sir and Dr. Rahul Bhattacharjee, for chairing this technical session 7. And I would also like to thank all the speakers of this session, all the oral presenter of this session for joining us in RPC 2026. Thank you very much for being with us. And I would like to thank our plenary session speaker, Professor Shantanu Ghosh also, and all the invited speakers, Dr. Navaparna Chakraborty, Dr. Devanjan Sen, and Dr. Suman Adhikari for delivering their invited talks. So thank you once again, and thank you very much. On behalf of organizing secretary, on behalf of Women's College Agartala, I would like to thank all of you for having with us. Thank you very much. Thank you once again.